So welcome everyone. We are already a bit late, so it's time to start. It's a pleasure to welcome you all at the reporting session of the Center for Theoretical Physics of the Polish Academy of Sciences. We are privileged to be here with representatives of other institutions. So first of all, I would like to welcome a representative of the third faculty of the Polish Academy of Sciences, Deputy Dean of the third faculty, Professor Konrad Banaszek. Many of you probably don't know, but some time ago, CFT was fighting for have full autonomy, and the third faculty played a pivotal role at that moment. We have also a representative of our big brother, so the Institute of Physics. So with us is a Deputy Director for Science, Professor Dewar. So welcome. So before we proceed with agenda, I would like to raise two remarks. This is our final gathering before Easter. So this is a religious holiday, but also it's very important in Polish tradition. It's time for new openings, for new hope, which is very important nowadays. And because of that, although we are not doing the traditional Easter celebration, but during the lunch we'll provide next to regular lunch also some traditional Polish dishes. And the second remark is that this reporting session formally is to communicate to the wider audience and to other scientists what we are doing. But in practice, we are also share what we are doing between us, and then we have the poster session. And also, this is the opportunity to discuss. So I hope that after this meeting, we'll have next discussions, more collaborations, but also some integration. And to facilitate that, we provide lunch, we provide then a bowling tournament in the evening, and there is poster session. So without the further delay, I will giving mic to the Deputy Director for Science, Remigiusz Augusiak, who will chair the sessions.
So hello, everybody. Because we are delayed a bit, we can start with the third topic, and so the speaker will be second. Okay, so the second will be presented by Karol Życzkowski, non-unitary evolution of quantum systems and the tree cube of Bronstein.
Thank you very much. So I'm going to tell you something about quantum systems, but in relation to free cube of Bronstein. So first, a very, very simple question. Who of you has ever heard about the name of Bronstein? Please raise your hand. One. Good, 2, 3, 4. Okay, so not all of you. I hope now you will see that it is an important issue, maybe even more important than quantum evolution. And indeed, I'm representing our task 2, complex systems and their applications. Marek Kusz is the leader, and first he would like to report 2 papers, as you see, published in computational biology, a hidden topology, a window into human perception. Interesting paper, I'm sure. Second one, consonances and correlations. You can check in the preprint from 2025. Now I have chosen some of our papers. I will not go through all of them. As you see, there are different papers. Somehow it happened that all of the journals are different. Topics are also different. I will only mention some keywords like quantum designs, fidelity decay, noisy quantum operations, entanglement witnesses, fractal spectral distributions, and channel non-locality. But I'm also very pleased and proud with the last paper. It's a really mathematical paper about numerical range with a serious mathematician. So Ilya Spitkowski from Odessa, for many years now in New York, he is really considered as a mathematician. So I'm pleased to have a paper with him. But now I will tell you something different. But we work at the center of theoretical, we work at the center for theoretical physics. Therefore, I will ask a bit strange, different question. What is at the center of theoretical physics? It's a very general question to all of you. Well, maybe not so well-formulated question, but if I now ask, what are 3 constants? They are just at the center of theoretical physics. What your reply might be? Yes, so there are three constants. If you check, if you ask artificial intelligence, you get exactly the same answer. Gravity constant G, speed of light C, and Planck constant H bar. So G and H are rather small in standard units, 10 to minus something. C is huge, but of course 1 over C is for me a small number. By the way, there is a strange difference. This is approximately equal, and you know, since 1983, this is exact result because you can say you can define time in such a way that C is exactly this number. But why those three numbers are important? This was the question posed before the Second World War by Maciej Petrovich Bronstein. He was born in Winnica, now Ukraine, arrested in Leningrad in August 37, executed in 38. So therefore, look how young he was. He was a colleague of Lev Landau, and he had a brilliant idea to basically describe all the entire theoretical physics in a cube. So in fact, it was at the beginning, in his picture, was a two-dimensional plot. Later, Zelmanov in 1967 formulated such a cube. I will show you. And this idea was not so well known, was later popularized by Okyun, a famous Russian physicist, and later by Stachel in 2021. Now it's much more well known in the West. So the idea is simple. We have such a cube, and then we rescale all those constants in natural units. So 1 is the actual value. And of course, 0, 0, 0 is a classical mechanics. Quantum mechanics is a transition along this axis. And in fact, in my research, I usually walk around this axis. Now, 1 over C is a special relativity. So if we say that C is going to infinity, so 1 over C to 0, you don't take into account those effects. And of course, general relativity is related to gravitational constant, and in a sense, this is the path studied by people working in general relativity. So in a sense, this is classical mechanics. Here is like on the opposite corner, theory of everything. So this is the actual physics where all those three numbers are non-zero. So now I can ask, we can make a very simple interview. So for whom of you those constants are important? As I mentioned, in my research, basically, I could do all my research assuming that C is equal to C is equal to infinity and G to 0. But because we have some people working on cosmology and astrophysics, so I'm pretty sure that all other parts of this cube are occupied in our center, and I think this is a nice way to place your interest in physics in such a cube. So more formally, you can ask in which part of theory those effects of gravity or relativistic of quantum effect play any role. So in a sense, in my research and work, I pose much more humble questions. So as I mentioned, I go only along this line. And now I will mention an analogy to this cube. So this cube is very, very general. Basically, in my opinion, concerns all of us, all of you. But now, in fact, I will use only analogy taken from this idea and apply to a relatively simple problem related to quantum theory. Quantum theory is, the modern quantum theory is 100 years old, and then you will know that this is the density matrix, this is the time evolution of the density matrix, and this is the famous Heisenberg equation, commutator of Hamiltonian withdrawal. And this leads to unitary dynamics, which we know very well. U is unitary evolution operator. Basically, then density matrix rotates like this. And after 50 years, exactly 50 years later, there was an important equation written, and in my opinion, it's one of the most important equations in the second half of quantum theory. And sometimes it's called Lindblad equation, but should be called GLKS because of Gorini, Kosakowski, Sudarshan, and Lindblad papers, which basically makes a generalization of this. So here we have such an evolution of density matrices for unitary dynamics, and there is a non-unitary dissipative part, and the key result, I will not go here into details, is that any evolution of quantum object which is non-unitary, but which preserves positivity, can be written in such a way. This is the more well-known diagonal part. So those VI are called jump operators, gamma are the decay rates, and this is very important that any evolution can be written in this way. So now so in fact this is called Kosakowski matrix, is positive, definite, and those gamma are eigenvalues of this matrix. This is diagonal form. And I think this is all what we need to know. So because I will only mention here Professor Kosakowski, who unfortunately passed away at the beginning of COVID in 2021. And now this operator can be written in the general operator form as a function of those jump operators and gammas. And then we can assume that we do not know nothing about those objects. We replace them by random matrices to find an ensemble of such dynamics. We can represent it by this is an approximated way to write it in random, in terms of random matrices, and we find the universal spectrum of eigenvalues of this operator in the complex plane, and this blue line is obtained analytically or semi-analytically, which is kind of a new universal result. And now, so here is just to show how to get it and how to approximate the original Lindblad operator with random matrix approximation. We use so-called Geneve ensemble, and C is just GOE, Gaussian orthogonal ensemble approximation. And then, what we now study is so-called super decoherence. So decoherence is to take the state into diagonal part, classical part. But you can also have super decoherence of quantum map or of Lindblad operator, which decoheres to Kolmogorov operator, which acts in the space of probability distributions. And then we observe a transition from the spectrum of this lemon-like shape into such a strange shape, which we call spindle, which is characteristic to classical random Kolmogorov operators. And there is another important issue, which is a special symmetry. Like you have a time reversal symmetry. Here is something which is called in statistical physics detailed balance symmetry or quantum detailed balance condition, which in a sense corresponds to assumption that something is symmetric. And then the spectrum of those Lindblad operators under this condition, they are real, not complex, but real. And this is related to so-called Davis semigroup or Davis evolution. And then we introduce only a single parameter which describes this breaking of the symmetry, which is just a ratio of two semi-axes of an ellipse. And then, in fact, we get an ensemble of such Lindblad operators, which depends on three parameters. P is classical parameter, which somehow scales this classical axis. So here it goes downwards. R is a rank of this matrix, which goes from 1 to n squared, and tau is the symmetry breaking. So here we have some analog of this Bronstein cube for our Lindblad operators, and in principle, any point inside cube represents one ensemble. So this is like a generic case for which we have lemon spectra, and now for each point of this cube, we can find different ensembles, different properties, and we can try to describe spectra. Here I will show you only, let's say this is one face of this cube, and you see the strategy of how the spectra change along two axes. Here are complex, here they are real, so this is only density of those eigenvalues. And in short, this is I believe, interesting way to describe non-unitary random, in general, non-unitary Lindblad evolution. And I think this is the end of my story.
Thank you. Are there any questions?
Here are only concluding remarks, which I skipped, but in short, it's, I think, nice analogy to this work on quantum non-unitary evolution to the general free cube of Bronstein.
So I had a question. So I think the Lindblad equation type thing assumes that it's Markovian, right? Or something.
Sorry, not what?
So this Lindblad formulation assumes that the system is Markovian.
Yeah. Okay.
Yeah. So this is within the Markovian sort of subspace.
Yes. Very much so.
Thanks.
In fact, the main title of this work is The Many Facets of Markovian Generators. So this is everything under the Markovian approximation. Thank you very much.
Any other question?
Thank you very much. I will only mention my collaborators. Yes, here. Wojciech Tarnowski, Dariusz Ruściński, and Sergei Denisov. Sorry that I forgot about them.
Hi, Karol. So very nice talk, and I like the idea of this Bronstein cube. I would like to just give a comment that nowadays in modern astrophysics, we are actually at the corner of this cube because not only the GR and special relativity is important, but also quantum effects as well, such as the quantum kinetic effects, neutrino oscillations.
So you are just working in this somehow the most difficult corner
That's
of the
right.
cube. Thank you very much. Yes, so it's good to know. And I think it's nice somehow that you can localize your interest in physics into different parts of the cube, and you occupy this most ambitious corner. Thank you very much.
Okay, thank you for all the questions, and let's thank Karol again for his inspiring talk. We now move to the third topic. The talk will be given by Krzysztof Pawłowski. Okay, Krzysztof, the floor is yours. You have 12 minutes.
Okay, I'll try to be on time. So thank you for the introduction. And my talk is organized in a different way. So first I will comment all achievements of the group, and I will just flash some results. So this is our group. It's led by me and Professor Żążewski. Maciek Marciniak finished his PhD last year, and now he's about to work for Google. But 2 PhD students joined, so Mateusz and Szymon, they are here. Bura now is at the Institute of Physics, and we have 2 senior researchers from Ukraine, Victor and Oleg was partially visitor, partially employed, and also students, Zuzanna Kurkowska, Jan Okoński, and Świątek from Warsaw University, and Maciek Kruk from IFPAN is also working with us. And we are founded by National Science Center, but from different projects. I finished now Sonata BIS, Victor had Polones BIS, and Professor Żążewski Opus. Unfortunately, these 2 projects are finished, and we have only one. So last year I received Opus. Well, 2 years ago, but started last year. Okay. Publications. So our highlight of last year is this publication. It's a review paper. The content is based on our efforts since 3 decades, probably, or even more. I don't know. So many people participated in the content. The reports on progress in physics is quite a good journal with high impact factor, so I hope it will play important role, this paper for the community. Then we have 5 other papers in Physical Review A, Physical Review Research, and Journal of Physics B. Some of them will be mentioned later. Other activities, so we are this group which was responsible for organizing Science Festival at CFT. This was done by Maciek Marciniak. We're quite involved in science popularization, giving workshops on quantum cryptography, lectures, and some interviews. We also organized a conference. It was organized in Paris, by the way, together with the Institute of Physics and the Scientific Station at Paris, and also the city of Paris was organizer. And we are supporting and benefiting from other projects like this Quantum Modeling Center, which is about to appear in ERA-CHOICE project. So this was like the summary of our activities from the last year, and now a little bit of science. But I decided to start from the very basics. So to answer the question, what we are doing, what is our interest. So our subject of interest is this, so the cloud of atoms, neutral atoms. If you think in quantum way, you think in the spectrum, and then each physical system is as a configuration, is represented as a configuration when you put atoms into energy levels, but at some temperature, below some critical temperature, abruptly all atoms, or almost all atoms, starts to occupy the lowest state, and this is called Bose-Einstein condensation. You can think about it in different way. So this is the picture borrowed from the lecture notes of Nobel Prize laureate Wolfgang Ketterle. So he reminds us that atoms are also waves, not only particles. And if the length of the wavelength, the Broglie wavelength, is larger than the distance between atoms, that may happen at low temperature. Then, if further these particles are bosons, then they interfere constructively. It's happening, they form big matter wave, which is also called Bose-Einstein condensation. This way or another, the system is real. It's created in laboratories. It was measured in 1995. It's used for superfluidity, supersolidity, nonlinear matter waves, and many other things. Now also in quantum technologies, so in gravitometers, and at least one gravitometer with BEC is at work. It's in Warsaw. It's used, and there are simulators and computers on the way. Sometimes people are saying that this system is not scalable, so I wanted to show you this picture, which is actually part of the system containing more than 300,000 tweezers with Rydberg atoms. This is from last year. So we can think that, okay, the system is well studied. It's entering now some technologies. So is there a place for theoretician here? Well, there are from time to time some surprising effects like this one. In 2008, people did the experiments in which they simulate supernova. So in cold atoms, you can control everything, almost everything. Also, interaction between atoms. You can make the atoms attract each other. So here the cloud was collapsing, cloud of atoms, and then exploding. And this is theory, so simulation. This is experiment. You see everything is matching. And this was for atoms with magnetic moment, substantial magnetic moment. Okay, but in 2016, people were repeating the experiment, but this time for dysprosium atoms. And instead of this implosion and this explosion, they measured that. So this is just a picture of atoms, and you see some concentration. And for 1 year, it was not known what's here. The measurement was done, by the way, by Tillman-Pfau from Stuttgart. And then it turned out that these are quantum droplets. That is a phase of matter that was not expected here. It contains each of them like 2,000 atoms, more or less, which form a superfluid phase, and they are stabilized due to some so-called quantum fluctuations. So we entered the subject because we also work on quantum many-body physics, and we wanted to understand these droplets in 1D. Well, first to check if they exist in 1D, and then maybe understand them better. So the first question you have to ask is, what is 1D, given the fact that we are in three-dimensional world? In practice, people are trapping atoms in very elongated, narrow traps, such that the atoms move along mostly along one direction. But then, although we know very well the interaction between atoms in 3 dimensions, it was not known how the atoms interact, dipolar atoms, in such confined geometry. So this is what we attacked. And with the help of people from Warsaw University, finally we managed to do the calculation and to construct the model, so to map 3-dimensional parameters into effective 1-dimensional model for dysprosium and erbium atoms, and these are these atoms that are used. And although the paper landed in Physical Review A, but it was suggested by the editor to others. Okay, we know how the atoms interact, so we can look whether they can form a droplet in 1D. So the answer was already known, that they should form a droplet. This is density versus position, and you see that under some conditions, the atoms form such a profile, so there is flat top. It looks like a droplet on a table. Yes, it's flat on the top. But this is 1D. There is no phase transition. It's just smooth transition, crossover between some bound state solitons and these droplets. So we constructed phase diagram, and this blue narrow region is the region more or less where the droplets can appear. And we also propose an experiment, I think very funny one. So if you have 1D and you polarized magnetic moments of atoms perpendicular to the trap, then the atom can be in the gaseous phase. And then if you smoothly change the polarization of atoms just by changing the external magnetic field, then the atoms can go from gas to these droplets, from the gas to a liquid, just by changing the magnetic field. So this is something we proposed in this paper. I hope there will be some experiment at some point. And my time is almost over, probably.
Still 3 minutes.
So I thought it would be longer. So the last paper from last year related to this subject of droplets is this one. We wanted also to study excitations of a droplet. So what you see here are excitations, well, subsequent excitations. So I is just labeling the first, the second, the third excitation mode. And what you see is, what we checked actually, that these excitations, they have dependence of the energy with respect to momentum, which is linear, what means that this is superfluid. But funny thing with droplet, this quantum droplet, is that the number of excitation modes is finite. So if you add too much energy, the atoms inside, they cannot produce quick phonons inside. Instead, they emit atoms which are going out of a droplet. So we were able to compute the maximum number of fluctuations. We're also able to compute the just size of the droplets. So in this paper, we did a lot of analysis to compute like the most simple things for these droplets in certain regimes. I have to say in the regimes in which the droplets are composed from strongly interacting atoms. So with that, I would like to save your time. It's a bit faster than I expected. So thank you for your attention, and now we have time for questions.
Thank you, Krzysztof, for your nice talk. I open the discussion. I guess there will be numerous questions.
Thank you, Krzysztof, for a nice talk. I have two questions about droplets. So first, does it make sense to define surface tension and like in this context, and do quantum effects affect it? And second, did people study like, I know, coalescence interactions of many droplets, like sort of in a like mesoscopic hydrodynamic setting?
Okay,
maybe some funny playground.
Actually, this is a very good question. Namely, yes, one can think about the droplet in a classical way. So look at the surface energy, bulk energy, compare different energy scale. You'll find that often this surface energy is very small. It has consequences that it will be easy to split a droplet into many droplets. And this is touching your second question, but also it's experimental problem to have a single droplet and to study these droplets in 1D carefully. It seems that in a 2D and 3D, this is not a problem. So there's a single stable droplet or just a couple of them. But although in 1D there are experiments in this regime, so far no one have shown nice droplet. And maybe because of that, because they have many of them in random positions and they can study them.
Any other question? So maybe I ask about this gravitometer. So you mentioned that in Warsaw there is one. So what do they use it for? Do they measure with that?
Actually, I heard their talk two or three times. So there is the Institute of Geophysics, but not the one of the Polish Academy of Science, another one. And they can measure very precisely acceleration. And they have many different devices. Some are very stable, so they can take the device to another place and measure this gravity and look also what is under the Earth, actually, under the surface. And because of that, they also bought this quantum gravitometer just to benchmark it, I think, with the other devices. And the conclusion is that in some respects it's better than the classical devices, but it's not very stable. And if you look at, if you have the device which is in one place for a long time, still there are better devices. But maybe you can invite them to CFT.
Exactly, yes.
They will tell us.
Okay, let's thank Krzysztof again. And I would like to invite Bożena Czerny, who will tell us about the astrophysics groups and other astrophysics research in our institute.
Okay. So I will report for this topic 4. The leader of the topic is Agnieszka Janiuk. but our group consists of two subgroups, I would say, both in astrophysics, but Agnieszka concentrates more on galactic sources, and my group concentrates more on active galactic nuclei. So my group is shrinking, group of Agnieszka is growing for obvious reason. So I start with my group. You see the list of people, and later I will concentrate on paper number 2. Okay, so still some papers. This paper number 7 is for 200 points, nice. And there are 3 new papers in press, and one is actually with Agnieszka, so we collaborate. And I have no posters because my group is shrinking, so there is nobody to do the poster, and I was too lazy to do the poster. Those are publications from Agnieszka group, and they provide 4 posters. So I will concentrate on paper number 2 from my group for 2 reasons. One, that Vikram has just defended his PhD in front of the committee, and I hope that a scientific council will approve that. And second reason is that this is very important paper for our group, and we were working to achieve this goal since several years. So our goal is to measure the Hubble constant, and Hubble constant in astronomy is measured, comes from the measurement of the distance. And one of the methods to measure the distance comes from the measurement of the absolute luminosity, because it's easy to measure the local observed flux. If you know the absolute luminosity, you calculate square root, you have to remember about pi or something like that, and all is done. So the problem is to determine the absolute luminosity of active galactic nuclei, because we do use active galactic nuclei. And we developed a theory which relates the absolute luminosity of the active nuclei with the absolute size of each of elements. It's a complicated system. So the system consists of a black hole, of an accretion disk, of outer dusty torus, and critically of clouds, broad-line region clouds. Those clouds are important for our climate and weather prediction for tomorrow, but also in active galactic nuclei, those clouds are of extreme importance. The emission from the direct vicinity of a black hole is strongly variable, but we not only do see this emission directly, we see this emission reprocessed by the accretion disk, we see it reprocessed by those clouds. So in order to say that we understand the system, we have to understand the theory of the accretion disk, and we have to understand the theory of the cloud formation. And it took us really several years, because the theory of the cloud formation was proposed by me, my PhD student, in 2011. And the publication of using this model to Hubble constant determination was only published last year, with some strong fight with the referees who simply answered, "This cannot be done. So why you try?" Finally, we did publish, and we will continue. Because it's indeed quite complicated system. We had to describe the dynamics of those clouds. So formation mechanism, and we claim this is related to the dust formation and eventually dust sublimation, depending on the situation. So I agree, it's complex, but we did it. We did it. So how we do the distance measurement? Since, as I said, the internal emission close to the black hole is variable, we see the light echo. We see the light echo from the disk, from the clouds. And this light echo, those time delays are measured observationally. The paper which I discuss is based on time delay measurements, actually not done by us. It was taken from the literature. Now, this year, we have our own time delay measurements. So we will continue. But knowing this time delay measurements, we reconstructed the whole thing. We reconstructed the actual absolute luminosity of the source. And of course, it is quite complicated because as you can see, I don't think I can describe all those things in detail. The middle panel is the optical UV spectrum, which consists of several components. The upper panel are time delay in several bands. And we model each wiggling, and this is due to the reprocessing by clouds and the presence of dust and atomic physics, etc. So as Agnieszka said, in this model, we also use G, C, and H because we use atomic physics. The lower panel is just the broadband spectrum, including X-rays, warm corona, whatever. So how we do that? We fit the spectrum, we fit the time delay, and we calculate chi-square, and we minimize that for assuming distance as an arbitrary distance, and we minimize this, and from this minimum, this is the right-hand side plot, we determine the best distance, and best distance is easily converted to Hubble constant, and we got more or less 67 in units, of course, extravagant, because astronomy always uses extravagant units, so kilometers per second per megaparsec. It should be only seconds to minus something, right? As kilometers should cancel with megaparsec, but in astronomy it does not. So this is the content, the result of the paper which Vikram Jaiswal presented as important part of his PhD thesis. And the last comment, why it is important. Who cares? Well, we have various methods of measuring the Hubble constant, and the basic method is from the microwave, cosmic microwave background. And if you measure the properties of cosmic microwave background and you extrapolate all those properties, you get the Hubble constant here. Now the accretion, the expansion rate of the universe. You get 67 with the error 0.5 or something equally small. Now there are other groups which use, for example, supernova 1A, excuse me, and they are getting 74 plus minus 0.5 or something. So this is the famous Hubble tension, and that implies that cosmological constant is not constant, and then you need new physics because it means it's an evolving scalar field or whatever. On the other hand, particularly local measurements are always biased. They can have systematic errors, although all authors always claim that they included all possible systematic errors. So we think that having an independent, completely independent method is useful. And our method gives 67 right now, consistent with Planck measurement, of course with large error, something like 10%. But within the ERC grant, we plan to measure 100 sources, so the error will drop by a factor of square root of 100, so it will be 1%, and there will be a Vera Rubin Observatory LSST data for from which we will have thousands of sources. So we hope to see the problem, whether we have Hubble tension or we don't. Personally, I'm not sure we have Hubble tension. Really systematic errors are very important. Thank you.
Okay, thank you very much. Questions?
Yeah, so we are for the 67. Why do you think, so do you think that this 74 is measured with not including all systematic errors? This will be the strong.
Yes. Yes, but
statement.
Of course the person who is advertising 74 is the guy who already got the Hubble Nobel Prize for the supernova 1A, and he wants to get the second Nobel Prize for discovering new physics. So he's pushing very strongly in this direction. Although the method uses so-called distance ladder. So you have to rescale one method to the other method and then to go to the supernova 1A. He claims he included all systematic errors. I know what are systematic errors in my method, but they don't even know the mechanism of the supernova 1A.
So it's very impressive that you have a new approach to get this number in a completely independent way. I'm impressed. I have a technical question, which is really intriguing me. So if you have the slide with the data, there are 3 points in the bottom of the dip here, yeah? And then the estimate that one has is 67 plus 10 minus 2. So I'm guessing that the 67 is the left point, and then you sort of look for how wide it is to the left and right side of that. But I wonder, like, just thinking, is it an algorithmic thing, or why do you actually take that left point instead of the average of those 3 on the bottom? Just thinking of this in the meta way for like general analysis of data.
Well, I was just conservative, so I did not try to push the error because I could do the parabolic fit and then insist that the error is much smaller. I don't want to do that.
Okay, so
it's a pilot study. We did show what we actually did. And now we are analyzing 2 more sources. We will have up to 100 sources, hopefully, in a small few years. Yeah, and then we can play with determination more carefully. But within this error, yes.
Okay, thanks.
You can do anything, yeah.
Any other question? I don't see now. Okay, now? Okay, so let's thank Bożena again. This was a very nice presentation. And now I propose that we move to the talk by Lech Mankiewicz about physics education in the era of artificial intelligence. And right after that, we go to the two online talks by Mikołaj and Paweł. So be prepared, people online. So Lech, you have 12 minutes and the floor is yours.
Thank you very much. I would like to talk about something different, basically about education, and just behind this fantastic research on the universe and questions about quantum physics. I just have been teaching for 7 years in a small primary school near Warsaw. That slide I should also tell you that I am not a stranger to what I'm talking about. I have accumulated certain experience and, slowly move in the understanding of how this whole very complicated system with a very strong influence of a human factor, sometimes unpredictable human factor, works. And that might be interesting for you because many of you have children in a school age, and there are also some of you who have grandchildren in the school age, so I think it could be interesting. And now about publications, well, this is not a topic you get easy publication in 200 points journal, but just by pure coincidence today in Plus Minus, addition to popular daily Rzeczpospolita is a long interview with myself about how do I perceive current situation in school and what eventually should be done to improve it. So I'm going to talk about the disruption introduced or perspective of disruption introduced by artificial intelligence, but I am not a stranger to technology as well. I, from the very beginning, as I entered school, being not really, without really a strong pedagogical background and knowing physics at the level of multi-loop Feynman diagrams or construction of robotic telescopes, I had really to learn the primary school physics from the scratch, and I did it from the internet, of course, where there are plenty of resources posted by very inspirational teachers who show what you can do. And also, I must say, I am very proud I developed a very strong school physics laboratory, very low-cost physics laboratory, and I will not elaborate on it further, but of course, this approach is, I think, much more efficient than spending thousands and thousands of Polish zlotys on so-called professional gadgets for school physics. Now, in a certain sense, our school, but I think all schools, and the most important is that from what I know from my bubble in Facebook, and all schools suffer now from a very strong problem. It started during the pandemic, where students couldn't really, were freed from control, and they discovered that they can do nothing, and teachers, of course, understood that there are bigger problems than say grades or progress, and that therefore they have to accept it. And the very basic purpose of school, which is to cultivate interest in the world, to cultivate curiosity, to cultivate understanding, evaporated. And nowadays, bound together with, I work in private school. It's not a literary school, but it's still private, so middle class. Parents have money and spend those money on providing a lot of extra activities. And as you all know, understanding requires reflection, and reflection requires time. And boredom actually is a time which you can spend on thinking about nothing, is also a mother of deep reflection. And that's all is missing. So the question is whether artificial intelligence can help us a little bit to solve those problems and also solve a problem of diversity. Because nowadays you have students with very different cognitive ability or level of mental development, simply. That's also because many parents rely on smartphones and instead of talking to their children, because they are busy making money to buy those smartphones, right? Now, all that started in August last year when both ChatGPT and Google, OpenAI and Google introduced a special mode in their artificial intelligence kind of chatbots, the learning mode, which especially filter out possibility of providing exact answers immediately, but engage the user in conversation. And in addition, Google with Gemini went further and created some additional tool, and just happened that our school uses the same Google framework as our institute, and therefore we have this Gemini in the version 3 or 3.5 for free. Normally you have to pay a small subscription. This is not the version Pro for $200 per month, but this one for $20 per month. But it's sufficient. Now what you can do, first of all, it changes economy of preparation. I can prepare various materials for my students, visualizations or even small games, basically within in the real time. If I see that something has not been understood or there is some mental barrier, I can really come home and prepare something interesting for the next lecture next week. This is done in natural language. You first discuss specification with your silicon assistant, and then gives it the same specification to create animation or visualization, or even you can create a game. Notion such like inertia is completely misunderstood, and if you keep asking questions and suggesting certain situations and asking what will be the outcome, you realize that although they can recite the first law of Newton, they still don't understand really, they don't feel what does inertia mean. And I created a game which basically amounted to moving masses in the outer space, and to show how different masses react to a force, right? Just as an animation. Now, those tutoring modes are also very, very important and interesting. And the final thing are assistants in the Google universe. You can create, configure an assistant, so-called gem, and it will talk to students along lines which you impose on it. Well, that works better or worse, but on the level of primary school, and with after a certain number of days of practice, it really works pretty well. So you can, for example, provide students with assistants which they can have on call, which is impossible in the case of human interaction, because although I try to be on call, of course they cannot ask me each time they have some question, because I'm not around. And that would really explain or provide some additional questions or pose some problems and somehow summarize their solution, and that can be sent to me and I can see the results. Now that means that basically students to much larger extent can find in this process what they really need and what fits their level of apprehension and understanding. And that's also very, very important and I think very useful. And the final check is that my students use these tools I built. And this is something which I just, sometimes I have a feeling that the main problem is just my own imagination. What can I propose or what can I design to close a gap which I see? And coming here with BAS, I understood that there will be a classroom project, so-called Klasówka, in 2 weeks, and I can actually create an assistant to help them prepare for that. And Now, these are my main results. I taught the whole class Sudoku, 6th grade, using an assistant, and that was very interesting experience. If some solving simple logical puzzles, basically, this is ideal tool. Important problem is that if they don't have really everyday intuition I used to have, so they mix the ideas of energy, force, and something, and it's very easy to create a teacher assistant who is going to talk with them about those notions and take care that they use it in proper contexts, right? And I also recently have started to use ChatGPT to design a special course from this mathematical laboratory class in 7th grade about graph theory. Everybody tells that we should teach graph theory, abstract concepts in the primary school, so I will try it. That looks already quite good. First of all, I had to learn graph theory, and I learned it from ChatGPT. And so this is my summary. The main problem, of course, is that you have to understand very well what you are doing and why you are doing this. What is your goal and what do you want to teach and what they should learn from you. And without that, of course, artificial intelligence can only sow confusion. But with that, this could be very helpful. And actually, I encourage you to find yourself a nice private school and start teaching. You will understand a lot about appreciation of science and logical reasoning in society. But of course, give yourself a few years first to investigate the environment, because I needed really a couple of years to really understand my role in all this business. Thank you very much.
Thank you. Okay, I guess there will be many questions. Why you sit at the end of the auditorium? I have to run a lot.
So thank you. Thank you for the very interesting talk. I mean, there are many questions. It's like a topic for long discussions. But one question I would like to ask is, you described the use of AI assistants and so on in the classroom. And can you say a couple of words about what was the student response to the environment and tools that you proposed? Was it successful or there were some issues?
Well, this is actually work in progress. It's fascinating because they have been confronted and I have been confronted with completely new technology. But a typical situation is that I configure this assistant in such a way that it ends, the conversation ends with a summary, and I ask students to make a screen, to dump the screen of this summary and send it to me, okay? And in most cases they do it, students do it, so that shows that they are somehow okay with that, and I learned something from those summaries. It is configured in such a way that it doesn't say that student failed, for example, right? But it says it does say certain code words which I pre-configured in order to inform me that something could be improved in student understanding, right? So in this sense, this is, I think, pretty useful tool. And they solve certain problems, they participate in certain games. I see that they do. And without that, I couldn't propose it to them, right? This is activity which does not fit in this by physical reason, cannot be applied in a usual static classroom. I need internet and I need some dynamical tool. And to create this tool in a time I have at my disposal, and given my skills, I need an assistance of artificial intelligence.
More questions?
Okay, thank you. So I want to ask you, have you investigated that if students spend time reading books and how this is compared to the time they spend in AI things? Because As I know, spend time and I is very time consuming to learn, to search. And so I want to know that if students still spend time to read books along with this kind of AI things or not. Thank you.
Well, our students do read books, and I provide them with ready tools. They don't have to design them from the scratch, right? So this factor that it shouldn't lead to taking too much of their time is included in design of this whole strategy. But and I know that we encourage our students. I encourage them every second lecture. Every second week, I ask them, what kind of book have you read during last 2 weeks? And we spent a few minutes on physics lesson about talking about that. And actually, in this community, students, most of them, of course, because they are such that don't read anything, and you see that. Most students do read books still. We also have had a ban on smartphones in school for 3 years now, I think, and it's working. I mean, this is a private school. They come to us from various locations, so they do need phones in their pockets. But those phones normally, or in their backpack, but those phones sleep there in those backpacks and they don't use it. On the other hand, we invested in some social structures, like places when they can sit, talk, or enjoy spending time outside, etc., right? So that's a whole strategy, but it works. And they don't lose time on smartphones, at least during school. But that's very funny, because just when they end and go outside the school gate, the first thing they do, they take out the smartphone from the pocket and open it. But then this ban is not working because it's outside the school gate.
Okay, last question.
I am surprised that that topic has...
Do we have any quantitative tests about the teaching efficiency? Here is my digression. Many years ago, there was astronomy in the 6th grade or something like that. And one representative of a Polish Astronomical Society asked children a simple question: do you like astronomy? And he separately asked that before the course of astronomy at school and after the course of astronomy at school. And what he noticed, studying several thousands of children, was the sudden drop in interest in astronomy after the course.
Okay, Bożena, to make a long topic short, because this is a very complicated question. We don't really have any valuable methods to test efficiency of the whole process. I claim that we spend 100 billion zlotys per year on nothing, basically. Because this whole idea that a student reads something and understands something immediately, this is not true. That most of you know, because you know how much effort it take to learn something and to understand something. But the whole educational system is mostly based on fiction, that once you tell something to your students, they will remember that, understand, and something like that. I put a lot of effort into designing non-efficient and so non-interfering, so to speak, non-invasive method into probing their knowledge. And therefore, I know how inefficient teacher am I. But that would be, of course, very interesting. There is now this push to reintroduce astronomy into a high school. And if there will be a group of professors who will just select topics from some book for astronomy students, the result will be disastrous.
Maybe
I can guarantee it.
Mm-hmm. Maybe they will ask ChatGPT. Okay, so let's thank Lech again. And now we can move. Now we can move to the online talks. So the first speaker will be Mikołaj Korzyński. Let's see whether we can hear him.
Can you hear me?
Yes, we can.
Okay, very well. I will share my
We don't see you. Okay, now we see you.
So I'm happy to report the topic number 1, theory of gravity, mathematical structure, astrophysical and cosmological applications. I will begin with basically describing the research areas of our topic. That's basically either applied general relativity, relativity applied to cosmology, light propagation in GR, gravitational lensing of electromagnetic and gravitational waves, and also mathematical relativity. So more conceptual and mathematical problems in general relativity. So this is the overview of the people we have currently in topic 1. As you can see, there are 3 research groups. The stars you see next to some people's names indicate that this is a person who joined our institute last year. So it's pretty obvious that quite a lot of things changed in the last year. I also included 2 former members with whom I still collaborate. Okay, so what happened during the last year? What were the most important events of 2025? So first of all, in April 2025, Professor Huszczo joined our institute, and he brought with him his ERC synergy grant, Gravitas, in collaboration with people from Munich, MIT, and from University of Vienna. He's building a new group, and he has recently employed 2 people, a PhD student and a postdoc. And the second important event is that I obtained the financing for my with Unisono project with Mariusz Ancha from Vienna University about lensing of electromagnetic and gravitational waves. And consequently, I also employed 2 people, Haider Han as my PhD student and Chris Harvey-Hawes as a postdoc. Regarding projects and collaboration, so my collaboration with Mariusz Ancha mainly focuses on lensing of gravitational and electromagnetic waves and generally wave propagation in curved spacetimes. And we have a 4-year financing for our joint project. Professor Huszczo has an ERC synergy grant. The topic is gravitational interferometry with entangled states in optical fibers. So basically using interferometry to learn something about gravity. He also has many other collaborators from all over the world. Professor Kijowski, who's the most senior person in our group, also has his international collaboration with the University of Leipzig and Sorbonne. I also have a long-lasting collaboration with Asta Heinesen from the Niels Bohr Institute, although there is no joint project. And the topic is redshift and position drifts in cosmography, and whether we can infer what kind of information we can infer from the composition of the Hubble law and the drift effects. Here are also the most important topics of Professor Kijowski's research: spin carried by graviton, evolution of gravitational fields, and also quantum physics versus non-flat structure of space-time. Last year, I also gave a 30-hour course on wave propagation in curved spacetimes at Faculty of Physics. Now the next thing is the papers. I'll just flash these slides for you. I will focus on this in this talk on this last paper over here, Position Drifts with Gaia, written in collaboration with people from the Niels Bohr Institute in Copenhagen. The topic is position drift with Gaia. I will explain what this paper is about. So this paper is under revision in Journal of Cosmology and Astrophysical Physics. I will explain why this is still the case. This paper is a continuation of our previous research with Asta Heinesen and her group. The topic is position drifts, or small variations of positions of very distant objects. What kind of signal can we expect if we try to measure them, and what we can learn from them? The previous papers were basically theoretical. In this one, we decided to work a little bit with data provided by the Gaia collaboration. So let me begin with a bit of theory. If you compute the variation of position of a distant source in a standard cosmological model, you can derive a fairly simple formula for that. What you see on the left-hand side is the drift rate, a vector which is orthogonal to your line of sight and which tells you how a source appears to be moving with respect to some kind of non-rotating frame in radians per year, for example. And the signal consists of three parts. The first one is entirely due to the observer's acceleration. It's basically the transverse component of the acceleration of the observer. And then there is two terms which consist of the source of the velocity of the light source, distant light source, and the velocity of the observer. These two last terms have certain coefficients in front of them, certain prefactors. You can think of these prefactors as basically 1 over the distance between the source and the observer. In cosmology, you have to be a little bit more careful what you mean by the distance. There's an appropriate distance measure which appears here. An important part is that the first term is completely distance independent. This first term is basically due to the known aberration effect. If you change your velocity, undergo acceleration, you see the apparent position of every source change a little bit, and this change is independent of how far your source is. Okay, it turns out that in the standard cosmological model, this acceleration term over here, acceleration with respect to something called the local Poisson frame, dominates by orders of magnitude over the other two terms. And within this acceleration term, the most important contributor is the acceleration of the solar system in the galactic gravitational potential. It is of the order of millimeters per second per year, so it's not a tremendous acceleration, and causes apparent displacement or drift of micro arc seconds per year. That's a very small angle. What is important is that it generates basically a dipole over the sky. If you take the displacements or the drift rates of objects all across the sky, this acceleration causes you perform a vector spherical harmonics decomposition, and this term over here is basically a poloidal dipole or a glide, and it's completely distance independent. No matter how far you are, there's an additional drift just because the observer is accelerating. This is way too small to be observed for a single source, even if you perform the observation for 10 or more years. But if you combine the information from many sources all over the sky, it turns out that you can measure that. In fact, that was measured before in radio astronomy. There were reports in 2011, 2012, and many others where people used historical data about the positions of distant objects, fitted a dipole profile, and managed to measure the acceleration of the solar system. The result was typically that it is directed indeed towards the galactic center, so this was the standard explanation. However, this was in radio astronomy. In the optical range, the measurement was done only quite recently by the Gaia mission, a space-based observatory, whose main purpose was astrometry, so determining very precisely the positions of millions of sources on the sky. And in the third data release of the Gaia mission, the Gaia collaboration also issued a paper about the measurement of acceleration of the solar system from Gaia astrometry. Basically, they picked up a large number of very distant sources, which basically served as a non-rotating cosmic reference frame, but you could also try to fit a dipole into their temporal variations and measure the acceleration. Now, the questions we wanted to address is whether we can detect any deviations from the standard model in this data, and in particular, is there any dependence of the glide on the source's distance? If glide is just an acceleration effect, there should be none. And the idea is very simple. We want to bin the distant sources according to the redshift or distance and check if the glide vector is consistent throughout the bins. And so the data we took is the official data from the release. It's over 1 million quasars, which Gaia used to establish this cosmic reference frame. The data that were available is the positions and the temporal variations of the positions, proper motions measured over a couple of years. And also Gaia could determine not very precisely, but whatever the redshifts or distances of most of these objects. And this is the data we used. The strategy was that we combine, first we fit a combination of low-order vector spherical harmonics to the full data set, just to see whether we recover the standard acceleration towards the galactic center, but then also fit the same combination of spherical harmonics to data divided into 3 redshift bins with roughly equal number of sources. And this way check consistency. Small problem is that we were scooped. There was a paper which did more or less the same thing, published 2 weeks before us or something like that. Fortunately, it didn't do exactly the same thing, and still, I believe our paper is valuable. By the way, this paper was published in Nature Astronomy, which is a pretty good journal. Okay, our analysis was a little bit different. First, let me mention the main result. So it turns out that there is a small jump in the amplitude of the glide between the first and the second bin. The first bin is basically sources which are from almost 0 to 1.25. And the 2 other bins from virtually from 1.25 to 2.2 and from 2.2 to 6. If you look more carefully, the plots over here show our results in greater detail, and on top of that, also the published Makarov's results. Here you have the particular components of the glide or the acceleration measured in the galactic coordinates. The x-coordinate points directly to the center of the galaxy. It is exactly in this component where we see again a jump between the first and the third bin. Makarov did not report this thing, but if you look carefully at the binning he used, this is not very surprising. Makarov did not consider sources with redshift smaller than 1 at all, and his bins were from 1 to 2 and from 2 to 3 and from 3 to infinity, which also has the disadvantage that the number of sources in each bin is very different, which also means that his last bin doesn't carry too much physical information. For the other 2 components, we don't see that much of an effect, except that there is some kind of small jump in the component Z orthogonal to the galactic plane. Okay, so key takeaways from this result. If you take the full data unbinned of the sample provided by Gaia, you get a reasonable agreement with the expected acceleration of the solar system, but there is a mild tension with the hypothesis of no redshift dependence. So there is the constant glide hypothesis is at 2 to 3 sigma level tension, and this is driven mainly by the component directed towards the galactic center. How do you interpret that? Well, we try to be conservative. Maybe some kind of unknown systematic in the Gaia observations, and there can be many because it's a complicated observation. But it also may be an evidence of new physics, some kind of large-scale motions, except that order of magnitude estimates don't really favor that because that would require pretty high velocities. Or maybe we need some kind of anisotropic cosmological model. We don't know. There should be more Gaia data releases coming, and we will certainly have a look at that data as well. Okay, thank you very much.
Thank you, Mikołaj. Questions, also from the online audience?
Thank you for a nice talk. So I would like to ask about the maybe explanation of this acceleration related drift, because it seems a little bit unintuitive to me. So is it a relativistic effect or just a classical wave effect, or maybe both? And can you somehow, in a simple terms, explain it? Thanks.
Okay, the answer is that it's something called the aberration effect, which is both. Basically, if you imagine 2 astronomers looking at the same star, one of them is at rest, the other one is slightly moving in a particular direction with respect to the first one. Both of them measure precisely the apparent position of a source. It turns out that it will be a little bit different. Basically, if you look at a photon moving in the x direction, okay, you have an observer looking at a photon moving in the x direction, and you have another observer which is moving with respect to the first one in the z direction. He will not assign the same components of momentum to the photon as the first one. Quite the contrary, the direction of motion will be slightly off, not just in the x direction, so to say. This is called the aberration effect, and it was already known, I think, in late 1700s. It was first measured. It was only due to the velocity of the motion of the annual motion of Earth around the Sun, and this is a very well-known effect. Now, what we see here is basically the same effect, but only due to the acceleration of the mainly the solar system in the galactic field, and to lesser extent, there is also contribution because of the acceleration of the galaxy itself in the local group, and maybe possibly other things. Is this explanation enough? Basically, a wave looks a bit different if you look at it in a moving frame. It has a different direction of propagation.
Okay, thank you. In the benefit of time, I propose that we move to the next talk. So let's thank Miko again. Pavel, are you with us?
Yes, I am, but I'm trying to. Can you see my?
Yes, everything is perfect. So you have 12 minutes, please.
So you can hear me, right?
Yes, we can hear you. We can see also your slides.
Okay, thank you very much. I would like to talk today or tell you something about something which I call the Beltrami-de model. It is the model that came to my mind some years ago, many years ago, about 10 years or even 15 years ago, when reading some old books in mathematics, especially the book by William Thurston on three-dimensional manifolds. And I get sources from various mathematicians, in particular Gilbert, Danny Hill, and eventually all this information that I had from mathematics was triggered by my chats and talks with Ted Newman and Roger Penrose. So somehow this thing was in my drawer for years, but I never had enough courage to just write it down and publish this thing. Now I'm old, so I don't care whatever people think about what I want to say. So it is why I just published eventually this paper. So the story will be about the Beltrami-de model. So I should first say a few words about what is de Sitter space. And this de Sitter space, strangely enough, it appeared very early in general relativity. It appeared in Einstein's de Sitter correspondence already in 1917. After Einstein realized that his static universe satisfies Einstein equations only if equations are corrected by the cosmological constant term, de Sitter just looked at these equations with cosmological constant term and found a strange solution with lambda, positive lambda, obtaining a curved spacetime with absolutely no matter. So that was already 1917, and he just wrote about this to Einstein. Einstein was not very happy with this. Actually, he didn't like this at all. It was something strange for Einstein that space-time can be curved by only itself. But so there was this solution in the air. Einstein and de Sitter were talking about this, but very quickly this solution went into oblivion because of Hubble's discovery of cosmic expansion. And at that moment, Einstein withdrew lambda from his Einstein equations, and the de Sitter space had no any reason to exist. Then it was resurrected, and it was resurrected, I think, only in 1980s when Linde started to introduce the term, I think, introduced inflation in cosmology to explain some very correlations in the let's say cosmic microwave background radiation between points very far away from each other. And for this, he just used actually de Sitter space to say that actually this de Sitter space was something that produced sudden expansion of the universe at the beginning. So that was the de Sitter space entered again to physics, and final resurrection was at the end of 20th century, as we heard today from Bożena Czerny, when one person got even Nobel Prize for discovering or for just claiming that universe has a cosmological constant and then this cosmological constant is positive. So at this moment, de Sitter space became very important because of the following fact, that de Sitter space, if you just consider Einstein equations without cosmological constant and without matter, so the simplest solution, absolutely simplest solution is Minkowski spacetime. And if you just consider Einstein equations with positive cosmological constant, then the simplest possible solution without matter is just de Sitter space. So somehow, if there is a cosmological constant, and some people believe that it will be always like this and it's just the same, so it means that eventually at the end of the universe should be a de Sitter space, because asymptotically it should just tend to de Sitter space. Okay, so it is how de Sitter space entered physics recently, and de Sitter space in my talk will be very much related to Penrose's conformal cyclic cosmology proposal. There is a mathematical fact telling you that if you have Einstein equations with positive cosmological constants, this positive cosmological constants makes conformal infinity, namely this the three-dimensional surface to which all light rays tend, or to which all light rays at which all light rays die. So positive cosmological constants makes this conformal infinity space-like. And this insight led Roger Penrose to conformal cyclic cosmology, the idea of conformally gluing the end of one universe to the Big Bang of the next. So somehow it is why, since this de Sitter space should be state of our universe at the very end, so if he glues something, he will be gluing it with the de Sitter space. So that's how de Sitter space appears in physics up to now, at least from my perspective. So let me now try to tell you how I would explain what the de Sitter space is for anybody. So there is some geometric way of describing de Sitter space, and I will just reveal this geometric way of introducing it now. Okay, so to describe what the de Sitter space is for a Lyman, just consider Euclidean space Rn. If you are a physicist or theoretical physicist, think about n equals 4. If you are just mathematician, think about any n. And if you are just if you just want to understand my talk, you can just think about n equal 2, because the construction is all the time the same, and everything what I'm saying for n equal 2 is actually valid for n equal n, whatever, and in particular 4, which would be the space-time dimension. So take Rn, so to define what the de Sitter space is geometrically, take Rn and just remove from it a ball of some radius, like say of radius 1, or in my picture, I removed from R2 a ball, a disk, okay, disk of radius 1. And now the model of de Sitter space is the complement of this ball in Rn. So Rn minus this ball will be the arena of my de Sitter space. And now, how would I define a Lorentzian structure on this Rn minus this ball? The causal structure is defined very simple. You just, to define causal structure, you need to define what are light cones. So what are line cones on this white space here? So very simple. You just say the rule is as follows. If you have any point in this n-dimensional space outside the ball, the light cone of this point is just a cone in this Rn passing through with vertex at this point and tangent to the ball. Okay. In this way, for every point in the Rn outside the ball, you have defined a cone, and you say that this cone is nothing else but the light cone. Okay. And if you do something like this tangency condition uniquely defines the conformal Lorentzian structure of this complement of this ball in Rn. And for example, in 2 dimensions, you can just write down, you can use some coordinate system, for example, Cartesian system centered at the center of the ball. And then in this Cartesian system, you can, by this condition, by saying that the light cones are just the cones tangent to the ball, you can just see what is the metric on this complement. And for example, in 2 dimensions, you get metric like this. And this metric is obviously, so in 2 dimensions, this metric is, you can see that it's obviously Lorentzian when you are outside the ball. And it turns out that this conformal structure has a particular conformal scale for which this metric is Einstein, and this Einstein metric is precisely the de Sitter metric outside the ball. So what is a de Sitter metric? The de Sitter metric is an Einstein metric outside a ball in Rn for which the light cones are cones tangent to the ball. That's it, okay?
Paweł, excuse me, 3 minutes, 3 minutes.
2 minutes more?
Yes. Yes.
Very good. Very good. So now the question is, do you believe that if I just define my conformal structure like this, do you believe that such space-time is good? I would say no, because now I have some missing piece, namely in my Rn I have a hole. So what can I do? Is our space-time perfect with this hollow hole? No. To complete the picture, we should fill this void. So if we just look at the metric, you will see that this metric actually, which is this metric blows up on the ball, but the metric is absolutely well defined inside the ball. So inside the ball there is still well defined metric. So actually this metric blows up. It has blowing up conformal factor on the boundary, but actually its conformal structure goes from the outside to the inside, and it's absolutely well defined. So this is just Penrose's realization of gluing 2 universes. One of them is the blue one outside the ball, and the other one inside the ball, and everything is just then smooth. The catch is that one unusual feature we have here, crossing the boundary into the hole, changes the signature of the metric from Lorentzian to Euclidean inside. So I will just call this thing, namely the entire Rn, with this metric outside being like here and inside being like here. I would call it the Beltrami de Sitter model. And this is because of Eugenio Beltrami, who first introduced this interior metric as a model for Lobachevsky space. So the beautiful simplicity of this model is that the geodesics for every point in this Rn now are just Euclidean straight lines, and outside they are distinguished into space-like, which are green lines, which are never intersecting the ball, null, which are touching the ball, and the red ones, which are time-like things. And that's precisely what I have. I have a somehow Riemannian Lorentzian hybrid with very nice and smooth geodesics everywhere, which are just Euclidean lines. And now the last thing, maybe I would say that in such model, I, for example, can have an observer here on the red line, which he just happily goes on his time-like geodesics. In infinite time, he eventually touches this. But conformally, he can pass through the Riemannian part and going further away. Maybe he appears there. So somehow there is something, again, in infinite time here, but in conformal finite time. So maybe I make last thing. There is this mystery. Cosmology requires vast amounts of dark matter, yet not such exotic particles have ever been found. So I would introduce a geometric hypothesis motivated by our model. What if dark matter is not a particle, but a distribution of localized Riemannian regions? Why it is dark then? Euclidean geometry lacks a time dimension, meaning no light cones. Light literally cannot propagate through these regions. So the punchline, such geometric inclusions would curve surrounding space-time while remaining fundamentally invisible. The adjective dark finds a purely geometric explanation in this kind of proposal. I think that I finish here. I have a lot to say, and I invite you all to read the paper in which much more about this is there. Thank you very much.
Thank you very much, Paweł. One short question. Quick one. You have to speak to the microphone because he...
Okay. So hello, Paweł. My simple question, what about anti? I mean, what is it related to
this will not work so beautifully. I'm sorry. It's actually fitting only to positive cosmological constants, really to de Sitter.
Okay, thank you. Let's thank Paweł again. Let's thank all the speakers of this of the first part of the session, and we can. Wojtek, sorry, but we have to interrupt now because there is a delay. So I would like to invite you for coffee now, and please be back here 12:10. So I think we can proceed with the second part of our session. And the first speaker of the second part is Oliver, who will tell us about, okay, your presentation is on, who will tell us about the achievements of the quantum mathematics and quantum computing groups. Yes.
Hello?
You have 12 minutes. The floor is yours.
Fantastic, yes. So I'm Oliver, and I am representing Starship Group 7. We are funded by all of these grants and projects, and maybe also some which I forgot, but these are the ones which I got from you. I think this is at least most of them. So who are we? In Group 7, we have 3 faculty members, Adam Sawicki, Iwo Błynski-Brula, and Michał Maszaniec, who run their respective groups, or subgroups. I don't know what the term is. So in Adam's group, last year was me and Oscar. I have since moved from Adam's group to Michał's group, but okay, in 2025, I was mostly in Adam's group, and we were implementing Adam's Opus grant. And in Michał's group, there's Marcin Kotowski, Daiki Struga, and Juan. I think most of whom are in the audience. Juan, I think, is currently away visiting a research institute elsewhere, but yeah. And we have a bunch of projects being implemented, all of which are very exciting, and some of which I know about. Okay. What did we do last year? We published 9 of these papers, and we submitted. We just put on archive the other 7. Most of them are pretty good. The Polish Ministry of Science and Higher Education produces these points, which they allocate to journals, which roughly correlate with how good your journal is and how good your paper is. So the mean number of points for these published papers last year, these 9, was 127, which as far as I'm aware is decent. There are 2, I think, which were published in journals that got 200 points, and the rest are sort of around the 100 mark. I am not going to talk about any of these papers in the remainder of my talk, in the scientific part of my talk, because I thought the most fun project that I was involved in last year is one that we haven't finished yet. And so we still have some polishing and some generalizations and some applications of our work that we want to work on. So the stuff that I'm going to talk about now is not yet one of these publications, but hopefully it will be next year. So next year we will include it. What am I going to talk about? I'm going to talk about some joint work that Michał and I did in collaboration with Chang-Hun Oh from Korea, who works at the Korean Institute of Advanced Studies, I think, KAIST, and Zoltan Zimobras, who works in Helsinki. These are both 2 very good scientists. I feel slightly out of my depth talking with them sometimes, but yeah, they're very smart. And we're working on some classical simulation algorithms for some particular quantum systems, or possibly some classical simulation algorithms for some particular class of quantum computers, if you want to call it like that. So before I talk about our work, I'm going to go back in time slightly and talk about this paper, which was put on arXiv on December 22nd of last year. It's published basically by two companies. This is a slightly strange thing in quantum computing, is that there are a bunch of companies doing pure kind of fundamental science now. So this is a collaboration between two of those companies, Phasecraft and Continuum, based in the UK. And the essence of the collaboration is that Continuum built a quantum computer and Phasecraft worked out a way to use it to simulate some interesting quantum system. And the interesting quantum system that they are simulating is the Hubbard model on this lattice. So some of you may know, some of you may not know, the Hubbard model is a model of basically electron dynamics, fermion dynamics, which you can essentially put on any graph. So here, each of these little points is a position where a fermion is allowed to be, an electron is allowed to be, and each line indicates the electron is allowed to jump from here to here. So in the Hubbard model, an electron can jump from this guy to this guy, but it can't jump from here to here in one go, right? These two are connected and these two are not. And yeah, for reasons of making things simple, they simulated on this like torus structure that makes things nice. Okay. So I should explicitly show the Hubbard model. I think it's not that exciting because the people who understand the Hamiltonian probably already know it, and the people who don't understand it won't understand it, but in any case I show it. This is essentially what the Hubbard model is. So this first term allows electrons to hop, to jump from site to site. And essentially, if you make this parameter here, j, bigger, they hop from site to site faster. And this u gives you an interaction between electrons on the same site. And I'm sure everyone here already knows the product exclusion principle, but electrons follow this anti-symmetric principle that basically say two electrons can never be in the same wave function, roughly speaking. In particular, two fermions cannot be on the same site with the same spin. And if more than one fermion is on the same site, then they need to have opposite spin. And so applying Pauli exclusion to this model basically says you can have at most two fermions on any site. And if you do have two fermions on a given site, they have opposite spin. So the interaction term ends up being the interaction between essentially a spin-up guy on a particular site and a spin-down guy on a particular site. The Hubbard model, I added these other names. It's always called the Hubbard model in literature. Actually, these two guys also independently introduced it, so I stuck their names as well. The Hubbard model has been applied to lots of things. It's kind of cool, mostly to the study of electrons moving around in systems, so basically in conductivity, or in some cases in the lack of conductivity. So the Hubbard model has been used to explain Mott insulators, which are a particular interesting class of insulator, and in some superconductivity studies as well. But yeah, so it's kind of quite widely applied. It's a fairly fundamental model in electron physics. I should briefly explain this thing about fermionic Gaussian stuff at the bottom. If U is 0 in this model and electrons just hop around from site to site without interacting with each other, this time evolution generated by this Hamiltonian is what we call fermionic Gaussian. I wrote the definition here. It doesn't matter so much. You can ignore it. The definition of fermionic Gaussian here means we can efficiently classically simulate it if it happens to be fermionic Gaussian, and we are in that regime exactly when U is 0 in this model. Okay. Why is this cool here? Because, okay, we can classically simulate when U is 0. We can also classically simulate things when U is not 0, but also not too big, essentially by writing things as combinations of things when U is 0. And that is what we proceed to do later. Does the previous slide mean that the Phasecraft paper is efficiently simulable when U is 0? No, it doesn't. And the reason it doesn't is because Phasecraft and Continuum picked an interesting initial state for their setup. They picked an initial state which is not fermionic Gaussian. And we only have efficient classical simulation from known results when you apply Gaussian operations to Gaussian states. Their initial state is some interesting correlated electron state, which is not Gaussian. It has some interesting, there's some physics reason why they care about these particular initial states they chose, but they turn out to be not Gaussian. And so standard methods for simulating fermionic linear optics don't work. They just break completely because the initial state is not Gaussian. However, Chang-Hun came up with a way which dramatically improves on the state of the art and essentially lets you classically simulate stuff where you have Gaussian operations applied to non-Gaussian initial states. And this was essentially completely impossible before Chang-Hun cooked this up. I'm not going to explain Chankin's method at all, because I have not so many minutes, and it's quite complicated. Roughly speaking, the sketch of the idea is he found a way to write these quantities of interest that you want to compute when you're doing a simulation as an average of some things which you can efficiently compute. And quite surprisingly, the variance, the average of some probability distribution, the variance turns out to be bounded quite nicely. Essentially, the variance is bounded by 1, and so you can apply concentration inequalities very naturally. So it's kind of not surprising that you can write this thing as an average. It's incredibly surprising that he managed to prove this variance bound that lets you get efficient estimation. At least incredibly surprising to me. So what can we do? If you have an initial magic state here, some fermionic Gaussian unitary, and this is just a Fock state essentially over here, we can compute up to error. I will explain these k in a second. You can compute up to this epsilon 2 to the minus k over 2, these kind of inner products in polynomial time with some small failure probability. And these guys, you don't get to the 2 to the minus k over 2, but you just get the epsilon. Okay. What is this k? These initial magic states essentially are built out of formally tensor products, but basically they're built out of blocks of individual little states, and there's k of those blocks. So if you have k blocks, you get 2 to the minus k over 2 simulation here. Okay, I've had 10 minutes. This is kind of interesting, actually, because it turns out that if you try and upper bound a quantity like this, essentially you've proved very relatively easily that this quantity cannot be bigger than 2 to the minus k over 2. And so epsilon 2 to the k to the minus 2, kind of the epsilon lets you just about become sensitive to where these things are, right? If this 2 to the k over 2 was anything bigger, then you would be essentially completely incapable of estimating these things to useful accuracy. This is exactly where it starts becoming interesting. Okay. Okay, so that's when U is 0. Still, the electrons still not talking to each other. The electrons still not interacting. So there is a way of getting around that and going from where the U is 0 case to where U is not 0, which I worked on basically last week. Essentially, you do another averaging argument, and you write the U is not 0 time evolution as an average of a bunch of U is 0 time evolutions, so of a bunch of evolutions where you can simulate efficiently. Unfortunately, there is not a similar variance band to what we have where U is 0, and the variance essentially blows up exponentially, which means you need an exponentially large number of samples to estimate these things. The exact parameters of the phasecraft continuum experiment, they ran in whatever natural units they had. They ran their time evolution for 2 units of time, where U is 4 up here. And unfortunately, to use our methods to simulate this, I think you would need about 10 to the 25 samples, which is a bit too many. That's a lot of samples. Realistically, you could probably do something around 10 to the 10 samples on a computer, like just a normal computer, which would get you about half a second worth of the time evolution in their experiment. So going from here to here, no idea. Maybe we can do that. 1 minute? Perfect, yeah. I think I finished. So yeah, these are future directions. We are trying to do better than this 10 to the 25 actively. We have some interesting things we're thinking about with the different classes of input states, what changes when you change the input state. And essentially, we have this hammer that Chankin essentially developed of how to simulate these things, and we're trying to find more nails to hit with our hammer. So these are some applications that we think we have for our hammer, but we are interested in finding some more. Thank you.
Thank you very much. Questions?
Okay, so these kind of models are quite popular in the community working on ultra-cold atoms. Mm-hmm. Therefore, I have a question: do you have collaborators from that community? And if you can, you are really trying to solve this problem on the classical computers and see how far you can go on the classical computer.
Yes, we are trying to come up with. So there are already, I should say, there are already very, very good ways of simulating these things on classical computers that people have developed. There's a huge area of things you can simulate. We are trying to just, slightly extend. We're trying to extend this the setup. So you can simulate slightly more things. But yeah. And no, we don't have any collaborators, I think, from the optical atom community right now, but I don't think we are opposed to having some.
Michał? This is your own work.
Yeah, but I just wanted to comment to address what Krzysiek asked, because like this type of Hamiltonian simulation fits into the scheme that we developed some years ago, like called fermion sampling, and we are working also. We want to work on extension to like Hamiltonian version of this scheme, and like potentially with Leticia Taylor from ICFO. Like she was interested in that, but let's say we want to develop the theory first, let's say, and we have some ideas how to do it.
Thank you for this explanation. People online, do you have any questions? Okay, so if there are no further questions, we can go to the next talk. Let's thank Oliver again. And the next talk actually will be given by me. So I will be my own chairman. No, I can be my own chair. Okay.
I can chair you, Remik, if you like.
No, I don't have to. I'm fine. I'm learning new skills, it seems. So, so my topic is the topic number 8, classical correlations in composite quantum systems. I'm going to talk about a result that I'm very happy about that we obtained with my previous PhD student, Ovidiusz. So we proved that all genuinely entangled stabilized subspaces are multipartite fully nonlocal. Okay, but let me start from the other slides. Okay, so this is the composition of my group in 2025. There were 5 postdocs, but two left, Piotr Mironowicz and Saronat. Saronat got a job in India, but then I have a new member, a new PhD student, Rito Prio. And then there were some students, 2 of them defended their bachelor. Okay, actually, Szymon Łysek defended his bachelor this year, and Jakub Szczepaniak last year. And 2 of them got a position in this Master in Quantum Technologies program of European Union, which is called QUARMEN, which is good. So this is, Jakub actually is the 3rd student that got to this program. So we were funded by 3 projects last year. The next, funded by the European Commission, which was a very nice project actually. It seems that using European money is sometimes simpler than using Polish money. Then there was this Sonata BIS project, and Quantera, 3 of them, I mean all of them, end this year, and in fact next already ended. But the other 2, so Quantera ends in March and Sonata BIS ends in August. So we are going to be smaller maybe. But luckily we got the International Research Agenda grant, a grant from this program to create a new unit within the Center for Theoretical Physics. We applied together with Michał Szmaniec and Michał Matuszewski. And well, we managed to get it. Krzysztof Pawłowski and Anka Reiter-Smilianic was also involved, and they were very helpful. So with all these forces, we were able to create a decent, let's say, proposal that was accepted by the Foundation for Polish Science. Now we have 30 million zloty to spend, and we have to struggle to spend it. And this is quite a challenge, I must say. Okay, this is our production in 2025. I'm going to present this paper. Let me just say that we had 4 papers for 200 points, which is good for the evaluation that is happening now. We had also some preprints. Okay, and let me go directly to the result. So as I said, we proved that all genuinely entangled stabilizer subspaces are multipartite fully nonlocal. Let me begin with some definitions to explain you what this is about. So we consider a multipartite state from a multi-qubit Hilbert space. We have n qubits, okay? And now the state is called genuinely multipartite entangled if you cannot write it as a tensor product of 2 other states with respect to any partition of all the parties into 2 non-trivial disjoint subgroups Q and Q bar. So if you have a state that cannot be written like this for any such bipartition, then you call it generally multipartite entangled. This is a very famous definition, which recently people started to question. And here at the bottom of the slide, you have two standard examples of such states, which is the Greenberg-Horn-Zeilinger state and the W state. Sometimes people say that W comes from the Reinhard-Werner. No, maybe it's true, but these are two good examples of such states. I mean, if you try, you will see that you cannot write it as a tensor product of any other two states. And then, so this was the first definition. The other definition is that of the genuinely multipartite locality. So I consider again my state psi, but now I let all the parties or observers to perform measurements on that state. So each party performs a measurement denoted by, labeled by X and obtains an outcome labeled by A. And the whole experiment is described by a collection of probability distributions where each probability is a probability of obtaining AI by party I when this party has performed a measurement labeled by Xi. Okay? So these are the correlations that are studied in a standard Bell experiment, multipartite Bell experiment. Now, if you are unable, there should be inequality here. If you are unable to represent these probabilities in this form, or in a more complicated formula that involves also convex mixtures of all such possibilities, then you know that you say that your correlation is generally multipartite non-local. So this is kind of the strongest form of non-local correlation that you can have in the multipartite scenario. It's very similar to the definition of genuinely multipartite entanglement. So these are two types of the strongest form of correlations in quantum systems, let's say. So now the main question is whether any genuinely multipartite entangled state is also genuinely multipartite non-local. So this is a very basic question that people have been trying to answer for years, and with some partial results, but not with a final conclusion. So given a multipartite generally entangled state, we would like to know whether it can give rise to correlation that is also generally multipartite non-local. This is sometimes called Gizen's conjecture. I'm not sure whether he posed this conjecture in any of his papers, but it's because he was the first to prove that in the bipartite case, every entangled state is also non-local. So he has these general results. The second paper is also with Asher Perez. And there were some other partial results about the multipartite case. So for instance, it's known that in the tripartite case, all genuinely multipartite entangled states are also genuinely multipartite non-local. Okay, so we wanted to somehow go in this direction, let's say. And well, why people care about this? This is because you can treat entanglement and Bernoulli locality as resources in two types of, or two frameworks of quantum information processing. So entanglement is a resource where you trust your devices. So when you know that your devices perform trusted measurements, I mean, so your measurement devices are well characterized and your sources are also well characterized, then you can use entanglement as a resource. And Bernoulli locality is a resource in a situation where you don't trust your devices. So for instance, you want to do quantum cryptography, you cannot trust the source of entangled states, you cannot trust the measurement devices, then you use Bernoulli locality. Okay? So now the question is simple. I mean, if I have an entangled state, which is useful in this device-dependent framework, whether I can also use it in the device-independent framework. Okay, so this is the result. So I'm faster than I expected. Maybe I can prepare some jokes for the end. Every state from a multi-qubit generally entangled stabilizer subspace is generally non-local. So this is what we prove. Stabilizer subspaces are known for their role in constructing quantum error correction codes. So this is a certain type of subspaces, and then within those subspaces you can find those which are generally multipartite entangled, meaning that every state from that subspace is generally multipartite entangled. So here is a picture, a very simple one. So you have a multipartite, multi-qubit Hilbert space, and you can find a subspace in that Hilbert space, which is composed only of generally multipartite entangled states. Okay, this is a an interesting feature of quantum theory, or Hilbert spaces, let's say, multipartite Hilbert spaces. And then what we proved that if we take such a stabilizer subspace, then each state in the subspace is not only generally entangled, but it's also generally multipartite nonlocal. But this also means that every mixed state acting on such a subspace will be generally multipartite nonlocal. So you can even imagine that you have a state which is the maximally mixed state on that subspace, and there are such states, which is a normalized projection onto the subspace. And you know that the state is generally multipartite nonlocal. So it gives rise to the strongest form of nonlocality. And in fact, we prove a bit stronger result, which is that all of them are fully nonlocal. So if you find this probability distributions, then you are unable to decompose it in terms of something that is generally multipartite nonlocal and something that can be represented with local hidden variable models. So this is the top, in a way, of the non-locality in the multipartite case. Okay, this is my conclusion. So we have proven Gizen's conjecture, let's say, for multipartite stabilizer subspaces that are quite broad. This gives us classes of mixed states which are generally non-local, which is nice, and they're even fully non-local. So you have a mixed state, you have a maximally mixed state, which gives rise to full non-locality. That was quite unexpected, I would say. Now we are working on the full non-locality of partially entangled states in the bipartite scenario together with ICFO, and it seems that there are plenty of really nice results. This was another open problem that people haven't solved for many years, and well, sometimes it is like this, that you cannot solve something and someone comes and solves it very easily. And also we try to work on full non-locality. In this line of research, we try to work on full non-locality of multipartite states. So we want to somehow generalize this result to the multipartite case. Thank you very much. Questions?
Ja już przyjdę. Remik.
Quick one. If you could go back to slides, to those blue picture. So my question is very here, simple. What is the relative size of this dark blue to the light blue? As you can guess it, the question is concerning this let's say, relative dimension of this subspace, dark blue.
So the maximal dimension of this stabilizer generally entangled subspace is 2 to the n minus square root of n, more or less.
Yeah. So then this lower blue, basically this which is not in this set?
No, it's wrong. Yes, you're right. If you want to say that this,
I don't say it's wrong. I want to understand it.
But if you say that this size of the stabilizer subspace is too big, you're right. It should be. I mean, yes.
So we can improve this picture.
Yes, I will do it for the next session next year.
Okay. Some other questions? And from online audience, I will check. Okay, therefore I propose that we can thank the speaker again, to Remik.
And now we can move to the next talk by Wojtek Hellwing. The talk will be online. Wojtek, are you with us?
Yes, I'm always with you.
Yeah, that's nice. I'm very happy about that.
And I'm just really sorry that cannot be in person this time, but I hope I will deliver this painlessly for you all and interesting enough. So I guess I should share my screen, right?
Yes, please.
Okay, thank you very much. So this is topic 9, which is the computational cosmology. It's of course named differently in our documents, but this is what we do. We have a group that do computational cosmology, which is the new incarnation of physical cosmology, because nowadays to do physical cosmology, so basically connect the theory with observation, you do need a lot of computing. Just one slide to summarize 2025 for our group. We had 12 active group members, around 5 PhD students and 4 postdocs and 2 leaders. And then we have Maciek, Mariana, Oliver, Priyanka, Szymon, Antonella, Feven, Paweł, Anjita, Gursha Ranjit, Rasmus, and me. And a number of active students, some from Warsaw, Helsinki, and Madrid. We successfully had a very we had one PhD defense last year, and Paweł Drozda became Dr. Paweł Drozda, who unfortunately left science, and now I think he told me that he's very happy making career in this Polish space tech company. So you see, actually, research about universe can sometimes produce a very highly trained specialist that will improve our space tech economy in Poland. We foresee some transfers in 2026. Unfortunately, Mariana Group's 3 people will be leaving to another institute, which I will be very sorry, but we really hope to keep collaborate and have interesting projects going together. Oliver Newton was awarded Marie Curie individual fellowship, so he was a postdoc in our group. Now he moved to University of Surrey, and Priyanka Yalan is in a transit, I think, to Taiwan, or Thailand. If I got mistaken here, that's my bad. Scientifically, output was around 24 papers, which 13 of this was actually because mostly of the membership in large consortia. This is a strong point, especially of Maciej, who worked hard for many years to become a core member of the large consortia in cosmology, observational cosmology. But we have around 11 genuine in-house papers that present group results. I don't show you the list here, but you can read this in the report. Grant, we finished Sonata bis and Opus. We have ongoing Sonata and Sonata bis. No new grants for the moment, but stay tuned because some proposals have been written and also some proposals are under evaluation. So we hope to hear some good news, hopefully, at some point. Okay, today I wanted to talk to you quickly about the new result we obtained with Pavel, which was a part of his PhD thesis. Is basically, for me, it's very interesting that such a small group of 3 people can invent a new method that hopefully, and actually show promise to be, if applied to the very big data that are normally brought now by this multi-billion big observational campaigns in cosmology, can actually yield competitive constraints on some of the important parameters we measure in cosmology. And speaking of this, let me quickly recap that we heard a little bit about this from Bożena's talk as well. So we have an amazingly good model that describes the landscape structure of the universe, basically the background model. So expansion and history of the universe, from the Big Bang through some inflation, galaxy formation, to the epoch when the dark energy started accelerated expansion of the universe. And this model, at least until recently, had passed absurdly amount of the observational test, explained the physics of the oldest light in the universe, so microwave background, explained very well global geometry of the universe and the background model. But it has some problems. So it all works well when you assume general relativity, but then you pay the price that you need to fill in the tensor energy momentum tensor of the background universe. 68% with something called dark energy, and 27% with something we call dark matter. Both of these components are still not very well established physically what they are. We have some candidates, but nothing really proven. So it's ongoing, one of the biggest goals of the modern cosmology and also physical scientists to try to learn about this more and try to maybe falsify some models so we have left with fewer options and we understand what's happening actually. One thing to just bear in mind quickly, that this also works well when you apply GR for the background model, assume that is isotropic and homogeneous, and basically then you find very simple Friedman-Robertson-Lemaitre-Walker metric. But basically GR is a theory of metrics, so you have all this kind of a metric of space-time components, and both Lagrangian of matter, which includes dark matter, and also this lambda term as containing this 2 things that we are not sure what it is, dark energy or cosmological constant or dark matter. So bear in mind that this is important, that we need to make this assumption that we can describe the whole universe using GR and simple metric, but we pay the price by including these 2 stuff in the Lagrangian there. So just also bear in mind that why it's potentially also a risky that just doing this and forget about more Tesla. Because we actually could change either the theory or some of these components and arrive at a slightly different model, and maybe something that wouldn't be exactly GR, but also with much better observation, or maybe solve some of the puzzles. So I think theory change is very important. What freedom do we have that we can change general relativity and still describe well the universe? What experimental challenge we have that basically we need to explain, we need to kind of test this extrapolation, because we have a very strong GR test on very small scales. either solar system or close binary stars, neutron stars, black holes, but this is still much smaller than the horizons in cosmology. And we also have observational challenge, so we need to try to explain better what is responsible for the cosmic acceleration. So standardly, basically, in standard background model, we add lambda, which is the constitutional constant, and we have expanding background universe. We have some problem now because we know the Hubble tension. So it seems that we make some measurements and extrapolate within the same universe. It seems that current expansion rate, which is the Hubble function, Hubble parameter, doesn't match when you extrapolate from the early universe when the physics is simple to the whole past light cone, or you use just nearby observation. In the method, the paper I want to discuss quickly today with you is just something we do the next step. We just forget about the background. We know the background is there. We had some observations. Now we're going to consider the first next perturbation of the background, which would describe the evolution of the large-scale structure in which we know the galaxies reside. So large-scale structure we know that came about from the primordial fluctuation from the cosmic microwave background. I described basically this delta, this universal in cosmology is called overdensity fields. It just locally in Eulerian space measure the overdensity or underdensity with respect to the universe background mean, right? So this is rho locally by rho mean minus 1. So whenever delta is positive, you have an overdensity, probably in galaxy cluster. Whenever delta is negative, you are in the cosmic void or very underdense region. And usually this is described in cosmology in a very simple way. Basically, this is actually some rendering from simulation, but basically you can either measure this by measuring the power spectrum of these fluctuations of this overdensity field, both galaxies or dark matter. And if you go back to very simple linear perturbation theory, you can get some interesting, very simple evolution equation, which here you have a Hubble factor. So this is the differential equation that describes how your density field perturbations should evolve in the some otherwise homogeneous expanding background. And here, however, for example, sound speed, if you will have baryons, but on the cosmic scales, you basically we don't have a pressure, so this term is 0. So in linear theory, so basically you can solve this equation by substituting and find there's a growing mode solution and decaying mode solution. In cosmology, only growing mode solution is important because if you wait long enough, then decaying solutions are not important. And also in linear theory, you can see very important result that the velocity field is proportional to the density field, right, on linear scale. So that's why this F parameter is just the time derivative of this growing mode solution. So it tells you how effectively gravity over in the expanding background amplifies the motions and amplifies the structure. So this was called linear growth rate, and this is like a holy grail of the modern cosmology to measure this and for galaxy surveys from different epochs. So actually to understand how effectively we form structure to get completely orthogonal to the standard expansion history measurement of the universe of the parameters in cosmology and testing GR and testing dark energy models. So normally how it's done, basically you observe some galaxies in your survey and you can measure the excess probability of finding galaxy pair at some distance. This is correlated to the so-called correlation function or autocorrelation function, which is just a Fourier counterpart of the power spectrum. And you can correlate this correlation function to the the perturbation theory and this growth rate of structure. So again, how effectively gravity in our universe change the fluctuations to structure and motions. And this is basically what is usually shown in this multi-million-dollar worth results of survey. This parameter, which is multiplied by something called sigma 8, this is just normalization of the fluctuation of galaxies because galaxies are more clustered than the rest of the matter, so we need to take this account. And this is redshift, so basically the higher redshift, the further in time we see. And actually you have some GR result here, some data points and some competitive dark energy or modified gravity theories, and all looks maybe okay for us. But we have a problem with this because in order to get any point in this diagram, you need to have very complicated phenomenological mapping between what theory tells you, basically model of gravity, model of background, and what you observe. Because the problem is that this dynamics of growth of structure is imprinted in galaxy clustering in this line of sight coordinate of a galaxy, because we measure this substituting Hubble expansion, but we know the galaxies are moving because of the gravity. It's called so-called peculiar motions, and this distorts the distance on the line of sight, which is a nuisance, but also the main source of information. The problem is that this mapping is not shouldn't be basically agnostic about the theory of gravity and all of your background model. But most of the people that work in the big surveys basically do this, assuming that standard model works. And then actually then can arrive at the bias measurement of this important parameter. The other complication is that to be able to measure this power spectrum from galaxy clustering, you need to know very well what is the distribution of random pairs, because you always remember measure the excess probability with respect to the random pairs that you would expect for the Poisson process. And you have a holes because your telescope on the sky, because your telescope was not working this night, or basically maybe you have a very bright star from Milky Way that was obscuring. And the problem is that you have a kind of a Swiss cheese nightmare map of this, and you need to really take this into account to measure this without extra spurious effects. And it was always a problem to get this selection effects, which we call how many galaxies we don't see because our telescope is too weak, or how many galaxies we don't see because something obscures the sky, to begin under control. So we had this different idea with Pablo and Maciej that maybe we can measure similar signal if we just don't focus on the probability of the pairs, but we just measure just how many galaxies are in the ball on the sky. But actually the ball itself is just simple solution, and this was done before, but we know that because our galaxy positions are distorted along the line of sight, we kind of generalize this whole question, which is just probability of count in cells, to have elongated ellipsoids along the line of sight or squash ellipsoid perpendicular to the line of sight. So basically, this is the idea. You just measure how many galaxies you find in many balls you throw on the sky, ellipsoids you throw on the sky, and the PDF change. And basically, if you can measure this change of the shape with respect to some standard predictions by just looking for the higher moments. So basically, for the correlation function, it will be, if you average this over the volume, it would just tell you where the mean is. But obviously, if you have non-Gaussian distribution, mean is not enough to distinguish between this, because the gravity actually makes all distribution non-Gaussian in our universe, because it basically attracts and galaxies are clustering more and more, and then you have a bigger empty space, so this kind of asymmetry grows in. So we started considering skewness. The new added value is, first of all, to use this in the redshift space to generalize the shape of this cell, not to be spherical like everyone did before, but actually to allow it to have a different aspect ratio with respect to the line of sight. And this is something very nice, because if you recall here, this is the galaxy clustering. If we wouldn't have redshift space distortion, we always measure very precisely distance to the galaxy, and this is actual measured galaxy clustering. You see this kind of a elongated structure on the line of sight, which we call redshift space distortion. The fact that in the overdensity regions like galaxy cluster, galaxy have also this thermalized component velocity, which is decoupled from the gravity. So basically, you have a kind of thermal noise that looks like this elongated line of sight distribution. So okay, what you get from
Wojtek, 1 minute. Wojtek.
Okay, yes, I'm nearly finishing. So I'm skipping some of the mathematical formulas here, but basically we applied this to set of simulation. We also applied this to some perturbation theory, and we found very interesting results. So basically, with this new methodology, when you just use generalized ellipsoids, you get something like this. So this is the radius of the perpendicular line of sight of this ellipsoid of the cell. This is radius of your cell parallel to the line of sight, so you can vary this parameter. And different colors tells you different dark energy models of different models with a different growth rate of structure. This parameter that everyone wants to measure in cosmology. And we've shown that this is huge separation of the models. So we can, for example, draw a 3 megaparsec line here to focus on small scale. And you see these are 2 sigma levels of variation. So these are kind of a strong discrimination between the models. So this is completely independent of the problems that you don't need to account for that many holes and selection function, because you just measure the distribution of galaxies in different cells. We published this result last year. This is very encouraging that you have such a strong separation of models. And now we try to collect manpower to convince people from these big surveys to apply this method using the new state of, or we're going to do it ourselves if we get people. And stay tuned, because this is very promising to provide completely independent new way of measuring this important parameter cosmology. And why it's important? Because it can either distinguish between dark energy or lambda, and can also distinguish between GR or non-GR models in cosmology in completely different ways. So we are very happy to have this small result, and just looking forward to implement this with the big survey, not only the theory and simulation like we did so far. So thank you very much for your attention.
Thank you. One quick question. If not, let's move on to the next talk by Jarek Korbicz.
Thank you.
Thank you. Jarek Korbicz will tell us about teleportations under decoherence.
Hello, everyone. All right. Hello, I'm Jarek Korbicz. I'm leading the Open Quantum Systems and Quantum Foundations group. Maybe briefly about the group. It's a small group. We have Rajendra as a postdoc, who is working on algorithms under decoherence, but also on foundational questions, objectivity, and other foundational questions in quantum mechanics. Then we have Mohammad, who is PhD student working on or starting to work on objectivity. Then there is Tomek Bazylewicz, master student, who has been working with me for quite a few years right now. He's working on two subjects or two groups of subjects, so algorithm under decoherence, but also on quantum electrodynamics coupled to gravitation, especially linearized gravitation. Here I have to thank Professor Białnicki-Birula for sort of encouraging us to move into this direction. This is this problematic corner of the Bronstein cube. And then there is also Kacper Lubkowski, another master student, who is working on the theory of master equations, unravelings, and stuff like that. The past member who was still with us last year is Tae-Hoon Lee, who defended his PhD, and now is back in Korea. We are powered basically by one grant, which is Quant-ERA, on quantum coherences activation by open systems. Then there is also a small NCN Preludium Beast grant, and this is paying Mohammad's research on objectivity and spectrum broadcast structures. Publication list, it's not big because we unfortunately got stuck last year on a couple of difficult subjects. And with a small group, if you got stuck, you don't publish. Okay, but we hope not to make this mistake again, and we are now basically preparing the results that we managed to obtain last year. We are preparing it for publications, or actually some of them are already under consideration. Now, about my talk. First I advertised the decoherence influence on quantum teleportation, but I decided to change the topic. I decided not to bore you with another quantum information talk and tell you what we discovered, how various teleportation schemes respond to the presence of physically motivated environments. Maybe I'll do it next year, but I decided to share with you an observation which I made some time ago. It is unpublished. Maybe you will find it funny, maybe you will find it amusing. So is there some link between quantum potential and generative artificial intelligence? So first let me maybe introduce what quantum potential is, sometimes also called quantum pressure term. It's the weird term in the ordinary textbook Schrödinger equation, which basically is responsible for, let's say, all quantum. In particular, it is responsible for the linearity of the Schrödinger equation. This term was discovered long time ago, as you see, 1 year basically after or 2 years after discovering the Schrödinger equation by Madelung, who was the first, from what I understand, in splitting, in actually showing that a Schrödinger equation can lead to something which looks almost like which is almost being actually an important thing here, almost like a hydrodynamical model by splitting the wave function into the amplitude and phase. And what one gets is the ordinary continuity equation, and then something that looks like a Hamilton-Jacobi equation, but there is an extra term which is called quantum potential. You can see that this actually, for interpreted in the classical term, this looks extremely weird, because usually the probability distribution is completely independent from the dynamical law. Here, again, viewed in classical terms, this quantum potential sort of provides a feedback between the feedback from the probability distribution back to the dynamical law, which is the Hamilton-Jacobi equation. And it has a particular form, which basically, if you look at it, tells you nothing. It is what it is, okay? Well, this is a, as you can imagine, because this is so deeply rooted in all the quantum effects, and people were trying to understand what this quantum potential is, how to understand it. There is, I think, even a book written on the quantum potential, and from time to time there appear different views on what quantum potential is. So I wanted to show you one funny view which I developed. So the motivation came from the Nelson derivation of almost derivation of Schrödinger theory, which has to do with the stochastic processes. When one has a stochastic process, then one can, as we all know, the stochastic trajectories are not differentiable. However, one can still assign two velocities to every point, the so-called forward velocity and backward velocity. That's very easy to imagine if you draw a cusp. Then going a little bit forward in time, you will get one vector, but going a little bit backward in time, you will get another vector. Okay? Now, combining those velocity, one obtains something which is called drift velocity, which is basically dragging the probability distribution, which appears in the continuity equation. But most interestingly, if you take the difference, then there is something which is called osmotic velocity. And this really has to do with, from what I understand, my knowledge here about the osmotic processes is like close to zero, but from what I understand, this is really something that appears when one is studying the velocity of a solvent moving from a lower concentration to a higher concentration. You see that this is a gradient which is pointing towards the higher concentration, so the higher probability. But what is more interesting is that this is this osmotic velocity which makes a difference between ordinary smooth motion and stochastic motion. If the motion is smooth, then both velocities are the same, backward and forward, and this is basically zero. Okay, so no wonder that actually one can reformulate or rewrite quantum potential using the osmotic velocity. Okay, usually using solely the osmotic velocity. So this is some sort of indication that quantum potential, if you believe or if you sort of like provisionally take this stochastic interpretation, that this has to do somehow with the stochasticity or this time asymmetry in the stochastic process. In particular, it has two terms. So one looks like a kinetic term associated with the osmotic velocity, but it's with the wrong sign. And then there is a second term. There is also a connection to a Fisher information, but I'll skip it for now. Okay, so but still, again, all right, we have this formula. So what? Yeah, like what can we read from this formula? And then I accidentally stumbled across something that I must say I have absolutely no idea about. So forgive me my ignorance, but there is there are methods of generative artificial intelligence which are called diffusion models, which basically, from what I understand, they work like that. One takes the data and destroys it in a controllable way by adding noise until you get something like totally noisy, for example, totally noisy picture. Then, from this totally mixed, so to say, distribution, one samples a new data sample or a new sample distribution, and then starts a reverse process, denoising until reaching a new data. Okay. So those processes are described by something which is called score function, which is more, from my understanding, it's much better than the probability distribution because you don't have to care about the normalization. What it does, it measures like how close in probability are two neighboring points. Now, if you look at the score function, you will see that this is osmotic velocity down to some factor, which is actually h bar divided by m. Okay, so the score function looks very much like the osmotic velocity, and this was the thing that sort of caught my attention. But then one can ask, okay, so denoising the data in this generative AI, in these diffusion models, one has to somehow control. Yeah, one needs some sort of like a cost function to see how well every step of denoising is performing. And what one uses there is so-called objective function, which is basically measuring how far away are two score functions. Okay? Then one can perform a very simple integration by parts, which to my huge surprise got even a standalone publication in these diffusion models in 2005, and one can develop some sort of formula for that. Okay, now how to connect it to the quantum potential? This already looks sort of similar because there is a osmotic velocity squared plus the divergent of the osmotic velocity. Well, instead of the estimated probability which is used in the diffusion models, one can take a model of a delta function, Dirac delta function, okay, and construct the same objective function. Okay, the same objective function, it's almost the same. There is one subtlety, I will not go into it, but one construct the objective function and then sends the delta controlling parameter to 0. When you do it, you just get the quantum potential at a given point. Okay, so this gives a sort of like a funny interpretation that quantum potential actually compares the score function, so the relative probabilities of the actual quantum mechanical probability distribution, the one which comes from the Schrödinger equation and wave function, to a highly peaked one centered around the given point where you look at the quantum potential. So in a sense, this is a measure of how far away is the actual probability distribution predicted by Schrödinger equation, how far away it is from a completely peaked classical-like distribution. Okay, this is basically it. Of course, the question is it accidental or can it, well, it is accidental for sure, but can it be used in some way? One direction is, of course, to use it somehow maybe to ease the quantum simulations, but more interesting direction, perhaps one can sort of like inject back Schrödinger equation to help generative AI. So this is all that I wanted to present. Thank you.
Thank you very much. Questions?
For me, the most intriguing aspect of this quantum pressure term is a rho in the denominator. The fact that it's so important where there is probability is nearly 0. Do you have any thought about that?
Well, not much. Not much. The only thought comes from this sort of a different figure of merit. Instead of using the absolute probability, which measures basically what is the probability of a particle being in given point, one uses this relative probability where you compare the probabilities of being here and being a little bit far away, and you normalize it to the probability distribution. By this, actually, you can get rid of the normalization constant. So that's the only thing I can say, that this is some sort of a related, this rho in the denominator, this is related to some sort of a relative probability rather than absolute. That's all I can say. Thank you.
Wojtek?
Hey, Jarek, thank you very much. That was very interesting. I have a quick question for you. So, of course, the diffusion model will learn. You need to throw that data, it will learn and probably distinguish the probability between each other, and then you can relate it to the quantum potential, as you said. But, you know, you always risk that there's something we call explainability when you use AI, right? You can really train it on the data, you can make a mock data from equation, but it's hard to interpret. Do you have a plan, or have you heard about the fact that you can still compare distribution using more classical measure like a negentropy or Kolmogorov test, and maybe using both will allow you to test how AI where's actually physics there, right? Because with only diffusion model, you risk maybe that will be hard. It will do the job, but you will not know why.
Not really. I mean, not really, because all this learning, this like you say, hardcore AI part, this is hidden here in designing this reverse Markov process. So it is somehow hidden there, and here the learning of this parameter is some sort of like, I don't know, deep neural networks which are used for it. So my first answer would be not really, but I will actually have a question to you. Do you know diffusive models? If you do, I want to talk to you.
Well, just superficially. I'm not expert, but we should talk anyway. Probably.
Yeah, great. Thank you.
Okay, thank you for all the questions. Let's thank Jarek again. Let us move to the last talk of our today's session, which will be delivered by Michał Matuszewski.
Okay, so thank you for the introduction. So I will present on this session results of my group, which is Strong Light Matter group. So the group now consists of actually me and two postdocs, Amir Rahmani, Juan Camilo, and two assistants who are working on their PhD. So they are employed in our Pathfinder grants. So they are not formally part of the school, doctoral school, Karol and Stanisław. And actually in 2025 also Dogion was part of this group, but he moved into Germany later. So this is the list of publications. So I will talk, I had to choose some topics, so I will summarize this work done together with our colleagues from the University of Warsaw on polariton networks, but there were many works. We had actually another work by Juan Camilo, who was also want to highlight because he is sole author of a work which is worth 200 points, so it's quite an achievement. But maybe this work is more like our group, more people from our group participated. So as I mentioned, we realized these Pathfinder projects. We have 3 of them. 2 of them, Q1 and Condensate, are related to quantum machine learning. Pollard is more about classical machine learning. And there are different materials that so all those projects are collaboration between theory and experiments. So there's actually quite a lot of experiments going on. And from the beginning of this year, we are also part of Center for Quantum Enhanced Computing. So in this talk, this achievement that I will describe is about neural networks. So I will first introduce exciton-polaritons. Well, exciton-polaritons are quasi-particles, so particles that appear in the quantum description of the system in a system where light is strongly coupled to matter. What does it mean that it's strongly coupled? It means that the interaction between light and matter is stronger than decoherence. In this case, the eigenstates of the system become substantially different from what we get if we consider these two, let's say, light and matter separately. So, and then the modes can become hybridized. So in this example, there are many different types of polaritons, but we are considering exciton-polaritons. So excitons are sort of like bound states of light and holes in a semiconductor, which remind of a hydrogen atom. And they can interact, they have dipole moment, so they can interact strongly with light. And when we put such excitons in a microcavity, which is good enough, with high enough quality, it may happen that we have a strong coupling regime. And why we are interested in Exciton-polariton neural networks? Because we would like to introduce a method for computing which will solve some of the problems that we have here with electronics. So electrons are very good particles for information processing. They have substantial interactions, but at the same time, we have quite high losses, which lead to heating and all the problems with energy consumption. On the other hand, photons are excellent for communication of information. They have very low losses, but they don't want to interact normally. So to make them interact, we usually need to introduce some special media, nonlinear media, and use a lot of power, which is, again, not very effective. So the idea is that when we use polaritons, we have both of them at the same time, because this is a particle which has properties of both electrons and photons. So to see that this may work, you can consider such a simple photo experiment where we have this polariton microcavity. We inject a laser pulse and see what happens when this pulse passes through the cavity. And we get some phase shift, nonlinear phase shift that is dependent on the energy of the pulse. And to make useful computation, we need this pi phase shift to be around pi, because then we can build, for example, some gate or something like this. And it can be estimated that in the case of Exciton-polaritons, this corresponds to such a condition between the energy of interaction and the inverse lifetime, or the loss rate. So by such a simple estimation, we can say that this cost, energy cost, so the energy that we have to put inside, is about 4 orders of magnitude lower for polaritons than in other nonlinear materials. So this is the basis of our idea. And we use this idea to propose some computing schemes. For example, this is our first work from back to 2019, where we proposed using this polariton system of coupled polariton micropillars to perform some computing, for example, for recognition of images. So it turns out that if we look at the evolution of the system and apply so-called reservoir computing scheme, where we have learning only at the output layer of the system, not in the system itself, we can actually reach quite good accuracy rates. So this year, what is the achievement that I wanted to emphasize is that in collaboration with our colleagues from the University of Warsaw, from the group of Barbara Piętka, we designed and realized a system based on perovskites, so materials with very high interaction between light and matter, to produce a first working neural network at room temperature. So previously, all these networks that we produced were working in liquid helium temperature. So this is quite important for us because we, to make some practical device, of course, we need to have room temperature operational. Otherwise, it will be not very economically, let's say, attractive. So this is a classical network. It's not a quantum computer, so that's why we need something that is quite economical as well. So what we realized is a quite simple network. It's just a couple of neurons. But it turns out that by designing not only this network, but also choosing the right task for this network, we can show that it can achieve quite high accuracy. And so the task that we came up with is a rather practical task. So the task is about detecting certain shapes. So in this case, it was a shape like distinguishing between no object, small circle, large circle, or a square. And it turns out that it's quite even though it's a very simple task, it's quite a lot of computation because we have very many pixels in this in this graph. So it's not such a simple task for a computer. I mean, it is simple, but not the simplest one. And we showed that our network, which has just a couple of neurons, can solve this task efficiently. So it is accuracy of this predictions is significantly higher than linear classifiers, as we confirmed in the experiment. And at the same time, the optical energy that was used was about 17.5 femtojoules per operation, which is much lower than what we achieved before with cadmium telluride microcavities. And also, this is actually comparable energy cost for the memory store-based electronic neural networks, which are state-of-the-art networks for electronics. So for comparison, for example, in the best NVIDIA chips, this cost is about in the hundreds of femtojoules. Of course, here I'm only talking about optical energy because we also use a lot of electronic equipment around tools which make this cost much higher. So it's not like it's immediately better than you can immediately replace it with the computers, but it gives some hope that this system can actually be very efficient. Okay, so that's all. That's what I want to present. Thanks.
Thank you very much. Questions?
Why you propose this task for your neural network, not the standard ones like deciphering ciphers from handwritten notes or things like that?
So the standard test is this, for example, MNIST database, like what was shown here. But we wanted to come up with a task which first can be realized with a network which has just four nonlinear neurons. So we were very limited in the numbers of neurons in this hidden layer. It's not very easy to solve a task. And on the other hand, we wanted a task which will be difficult for a computer. So actually, there's a lot of computation up there and down there because we need to process a lot of pixels in this. So it is not very. So, for example, if we use a linear classifier, we get quite not such a good accuracy for this task. And for the MNIST task, we get linear classifier can do it with quite high accuracy. It's 92.5%. So actually, this task, it may seem simpler, but it's more difficult for a linear network than handwritten digit because it comes from the fact that we don't know where these objects are in the position. So in this case, we know these letters are centered, and that's why we can just measure intensity in central pixels which look like one, and it already gives us a lot of information. So that's why it's kind of easier task.
Other questions?
Thanks, it was interesting. I was trying to understand plot, I think B, on the last but one slide, where you show the accuracy against the epoch. So I think I don't fully understand this accuracy thing that's being measured because it looks like it goes above 1, which confused me slightly. So what exactly is this quantity and why is it above 1?
I don't think it goes above 1. I think
it's just the plots.
One is basically where this. So it means that in the simulation we get practically 100% accuracy, like what you can see. Mm-hmm. So this is basically where 1 is. Mm-hmm. In the experiment, we have some, error, noise, and so on. So the experiment dash line is a little bit below. And for the experiment, it's not shown in the function of epoch because we train this system on a computer. Mm-hmm. And for experiment, we just transfer these trained weights to the experiment and do the measurement once.
I see. Okay, thank you.
More questions? People online, do you have questions?
I may have maybe one. Okay. Sorry. Michał, how does exactly the activation of these neurons work in your neural network? Is it some kind of logistic function, or what's this nonlinearity like? Because neural networks require nonlinearity. What is the form of nonlinearity you have in your neurons?
This is actually shown in this slide. So as I mentioned, we had 4 neurons, and this response function for each neuron was measured and shown here. So you can see that this function resembles very much so-called leaky ReLU function, which means that the standard ReLU function is just 0 up to a certain point and then linear. So it's called rectified linear unit. And in this case, we also have like a second linear part. So this is a leaky ReLU.
Okay, let's thank Michał again and all the speakers of this the second part of the session. And now we will have to listen to me again. So I'm going to present a summary of our achievements. Last year. I have 10 minutes for that before the food. I know we are tired and probably hungry. Okay, so usually I was presenting a picture of us made in 2022. The picture is outdated now. So I decided for this one, this is the logo that you can see when you enter the 3rd floor of this building, which is good because now people, when they enter the 3rd floor, they really know where they are. Before it wasn't clear for them. So this is our production. Swap hands. This is our production in 2025. We had 108 articles. 12 of them were for 200 points. So this is some increase. There is some increase as compared to 2024. 61 articles for 140 points. This sounds very good. And in fact, as far as I remember, for the evaluation that we are undergoing now, we used only one paper for 100 points. The rest of papers were 200 or 140. Of course, we can still try to improve the ratio here. So you can kind of swap some of them here. And the score will be even higher. It seems that we are doing very well in terms of points for publications for the evaluation. And Krzysztof was mentioning this already several times. The number of researchers has increased, and this is because we got some new projects like the EU Central project or ERC Synergy. Also, the number of PhD students increased. Say it again. These are the grants that we were awarded in 2025. There are only 2 NCN grants, which is, in fact, we were awarded only one because the NCN Sonata by Patrick was moved from Jagiellonian University. So this is something which a little bit scares us, but I hope this will improve over the next years. We also got one project from NCBIR, which is a complementary funding for the Cats4Kea project by Michał Oszmaniec, which is financed by European Union. So this was kind of easy money in a way. We didn't have to struggle a lot to write the application. We got this map, which is called International Research Agendas Program, together with Michał Matuszewski, Michał Oszmaniec, but also Krzysztof Pawłowski and Anka. We were very helpful in writing the application. And this application is somehow a result of the fact that we also applied for Teaming for Excellence, went to the 2nd stage, so we kind of were in this type of mood where you try to apply for every possible grant. We also got ERC Synergy that was moved from the University of Vienna, and Euro QHPC integration, which is the project that is going to integrate us among all these places which will get quantum computers from AQT. This is also financed by European Union. So total number of projects is larger than last year, but you see, it doesn't look as rich as last year, a year before. So these are the highlights. This paper was already mentioned. This is a paper co-authored by Michał Matuszewski. There is also this paper that was also mentioned in the talk by Michał Matuszewski. So he was faster than me. It's a paper in Laser and Photonics Reviews by Juan Camilo Lopez Carreño, who is actually a postdoc of Michał Matuszewski. And there are two papers in Reports on Progress in Physics. One is a review, co-authored by Professor Życzkowski and Krzysztof Pawłowski, about the fluctuations of the number of atoms in the condensates, and the other one is by my group. So we wrote a paper together with my previous PhD student and one of the students who is now on the Quarman program. Unfortunately, I couldn't find a picture of Jakub. Okay, I was trying today in the morning, but I couldn't. And me you can see every day. So, okay, Magda is there, so we are supposed, I guess, to go for the food. So the project department is grew in 2025. We hired Dorota Sierak, who is a project financial coordinator now, but she also, because she was working for Foundation for Polish Science, she has a lot of knowledge about the ERA program of the foundation. So she also helps me with this new huge grant. And we also have Krzysztof Szczygielski, who is an assistant in the EU Central project. And it seems that new people are yet to come. So soon we will have new people in the project department. Then we accomplished the second part of the renovation of our floor, in third floor in this building. So we look now very pretty in all parts of the floor. And many thanks to Magda, who was coordinating the whole thing. And she told me that she used ChatGPT to remove the papers from the desk so that they look very nice. So this was a smart use of new technologies. And we had to build a new accountant department actually because of the problems that you heard already about many times. So we have Magdalena Kuap, deputy chief accountant, and Sebastian Caleta, accounting assistant. And we also, in December, we moved from the Warsaw University of Technology to the office building at Rzymowskiego. This office building these offices were using in 2024 for the previous renovation. Concerning science, we launched our EU Central project at the beginning of 2025. And this project will bring us new regulations and better administration. That's one of the legs of the project. The other leg is that we will have a new group at the institute, and now we are running the competition for the group leader for that group. So you are welcome to go for all the talks and ask questions. We organized a kickoff meeting because of this project. That was quite an event for us because we could get some publicity. We also gave several interviews for media. And we organized several study visits. So the first one was at UCL. It was in July, as far as I remember. The other one was at ICFO. So you can see Anya and Dominika talking to people from the project department at ICFO. And then the last one was in November. It was again at UCL, and Paulina and Kasia visited the team there to learn how to improve our administration and procedures. The next achievement is the fact that we got ERC synergy. We got it because Professor Huściel decided to move from Vienna to Warsaw. So we are now running the second ERC synergy, which is good, but I hope that we will be able at some point to get an individual ERC project, and I hope some of you will want to apply for one. I already did, and didn't get it, but we got a new researcher in our team, who is Patryk Lipka-Bartosik. He's going to create a group. He started to do that already. He's not with us today because his third kid was born recently, so he has to stay at home now. We also applied for Teaming for Excellence project, and we made to the second stage of that. So we are waiting for the results. The results will be at the end of April, as far as I understand. And then we got this huge grant And now we are creating Center for Quantum-Enabled Computing. This is the logo, let's say. If you have a better idea for it, we can still change it. It was just, so many thanks to both Michał's, Krzysiek, and Ania. This was quite some work to be done, but we managed to do that. Now the challenge is to spend this money in a proper way. We organized many conferences, or were involved in organizing many conferences. So I just picked 4 of them, the largest ones. So the first one is Polish-French Symposium, co-organized by Krzysiek. This is already a series of conferences, which is nice. The conferences are held in Paris at this Polish Academy of Sciences station there. But everybody can do that. I mean, if you would like to organize a conference there, you just have to submit an application, and they will do. They help, no? As far as I understand. There was also this astrophysics conference at CAMK, organized by us. So the main person was Agnieszka Janiuk. There was a conference on optics of excitons in confined systems, organized by Michał Matuszewski, and a quantum certification conference, which is the second edition of this initiative, which we organized actually here in this auditory in May last year. There were 3 PhD defenses. So first, Tae-Hun Lee. The supervisor was Jarek Korbicz. Then Maciej Marciniak. The supervisor was Krzysztof Pawłowski and Paweł Drozda, who had 2 supervisors, Wojciech Hellwing and Maciej Bilicki. And challenges: find new space. It seems that we are growing, and the fact that we got 30 million zlotys to spend implies that we will have to grow even more, and EU Central project will make us grow even more. So we need space. We submitted an application last year to the Ministry of Science for the purchase of a building. So we found a building, but it seems that the ministry is unable to decide whether they want to give us this money or not. So maybe the outcome will be, as far as I understand, it should be in June. It was supposed to be last year, but probably it will be in June. And the other challenge is to create this center, make it excellent, and sustain it. So this funds are only for 4 years. We have even less now, less time to spend. So it's unclear what comes next. If we build this place, it might be that we'll not get the other such projects. So okay, we will see. And I would like to thank everyone for coming, participating, giving the speeches. Thank you very much. That's all. Thank you very much.